Good morning. We are starting today our second wildfire-induced air pollution assessment and mitigation symposium. This is a symposium that is a cycle of symposia that have been funded by a project from the UC Office of the President under award LFR 2065-1032. This is the second of a series of three, this exciting symposium is also supported by the UC Davis Air Quality Research Center, the UC Davis Climate Adaptation Research Center, UC Davis College of Engineering, and the CITRIS and the Banatao Institute. I'm Michele Barbato, PI of the UCOP project, and one of the organizers of this symposium. And I welcome you all to the symposium. I think I see the number of participants increasing rapidly, so I'll probably wait 1 to 2 minutes before really starting the symposium to give everybody the possibility to enter. But I'd like to start by thanking everybody that is attending the symposium and everybody that is participating to the symposium. We have a very dense and rich series of technical presentations that will take us from the morning to the afternoon. So everybody, thank you again. So using this time, just to give an idea of our agenda, we will have some introductory opening remarks. We have two guests, the Dean of the College of Engineering, Dr. Richard Corsi, and the Executive Director of CITRIS and the Banatao Institute, Dr. Camille Crittenden, who I'll introduce in a little bit. And then we'll have several technical presentations organized around 4 different themes. The first theme is wildfire modeling and forecast, considering changing climate conditions. The second is wildfire health effects assessment. The third series of topics will be around the wildfire emission prediction and assessment of air quality. And the fourth series of topics will be around the development and assessment of wildfire mitigation strategies. There will be some closing remark and an overview of the future activities for this project, as well as for the organization of the third symposium. And then I'll be available after the end of all of the presentations for additional questions if you may have any questions. So we are at 9:05. Let me start with some virtual housekeeping information. All of the attendees of the symposium are in listen-only mode. We are recording this meeting and it will be made available on the web page of the Climate Adaptation Research Center at UC Davis within probably a week or so. Feel free to use the question and answers box to pose questions to the presenters during the presentation. Each presentation will have a question and answer period after to allow for a lively discussion. The chat will be used for asking for tech support or for engaging in the discussion with the fellow attendees. Please change your to address in the chat to all panelists and attendees so that you'll be able to contact everybody that you would like to contact. I think we can go to the next one, and so without further ado, I'd like to introduce the Dean of the College of Engineering at the University of California, Davis, Dr. Richard Corsi. Dr. Rick Corsi received his bachelor degree, Bachelor of Science in Environmental Resources Engineering from Humboldt State University. These MS and PhD degrees in Civil and Environmental Engineering from UC Davis. He was instrumental in helping develop a new environmental engineering program at the University of Guelph and build a research program there that focused on gas liquid mass transfers and the emission of toxic chemicals from municipal wastewater. He later joined the Department of Civil Architecture and Environmental Engineering at the University of Texas at Austin. He joined UC Davis as Dean of the College of Engineering in September 2021. Dr. Corsi has been engaged in national discussions to layered risk reduction to reduce emission of COVID-19 by aerosol particles, including webinar hosted by the National Academies, UCEPA, National Tribal Air Association, and more, as well as more than 100 print, television, and podcast interviews. Early in the pandemics, his efforts focused on lowering inhalation dose of virus-laden aerosol particle indoors. He led an effort to develop an educational tool for assessing parallel intervention for lowering inhalation dose for aerosols and risk of infection in buildings. His concept of a low-cost and effective do-it-yourself air cleaner to combat virus-laden aerosol particles and wildfire smoke has become known worldwide as the Corsi-Rosenthal box. And with this, I'd like to welcome and thank Dr. Rick Corsi. Thank you.
Yeah, thank you for that really nice introduction, Michele. And thank you for the invitation to say a few words to kick off the second wildfire-induced air pollution assessment and mitigation symposium. As Dean, I'll admit this to you, I'm asked to speak at a lot of events, but this topic is actually one that I understand, which I can't say is true for many cases, but please keep that confidential. I wish I had time to attend the entire symposium. It looks like you'll be addressing some really important topics and you have some great speakers. So wildfires cause a wide spectrum of adverse impacts, from disruption of ecosystems to lost property and life, morbidity and mortality associated with inhalation of wildfire smoke, and the time-varying composition of wildfire smoke, population displacement, contamination of water, economic losses, stresses on healthcare systems, visibility reduction. The list goes on and on and on. And there's so much more here, but I'm sure all of
I think we may have lost Dean Corsi for a moment.
Am I back in?
Yes.
Yes.
Okay. I'm sorry about that. Where did I leave off? Where did my sound leave off?
You were saying that this is all of the effects of wildfire smoke and how they can affect health. And then
Okay. All right. Thanks. So I think where I hoped I was saying that please don't forget about indoor air quality to speak about wildfire smoke. My own field. You know, we are indoor creatures, Americans. We live to be 79 years old. We spend 69 of those years inside of buildings, 54 of those years inside of our own homes, and only a total of 6 years outdoors. And despite the fact that Americans are extreme indoor creatures, we become even more so during wildfire events. So building envelopes and interior sinks reduce fine particulate matter indoors relative to outdoors by about 50%. But when combined with the ratio of time spent indoors versus outdoors, again, much higher during wildfire events. And when we take into account our average respiratory minute volume indoors versus outdoors, it can be easily shown that our inhaled dose of particulate and gaseous components of wildfire smoke is dominated by what we breathe indoors. So buildings, the way we construct, operate, and maintain them, and the engineering controls that we use to remove air pollution during or following entry into buildings can play a central role in the extent of our inhaled dose of contaminants associated with wildfire smoke. Michele asked me to speak a bit about the College of Engineering's new strategic vision, and so I'll jump off of my indoor air quality soapbox now. The College of Engineering at UC Davis is undergoing a fairly intense grassroots strategic visioning process around three major pillars: research, education, and community engagement. We've lagged efforts associated with each pillar by 3 months, and we'll be unveiling the first one, our strategic research vision, in a couple of weeks. So please stay tuned. But the strategic research vision will inform faculty hiring, investments in infrastructure, new partnerships, seed funding, fundraising, and a lot more. It has 4 important vertical impact areas for which we strive to make major contributions and evolve as national, if not international, leaders in these areas. It also includes 3 cross-cutting themes that intersect with each of the 4 impact areas. Without getting into the complete construct of the research vision, I can provide a teaser and say that the topic of this symposium falls nicely into 2 of our 4 soon-to-be unveiled vertical impact areas. One is strengthening climate resilience, for which mitigation of wildfire effects is explicitly called out in the vision statement, and advancing human health. And one of our cross-cutting themes is technology for the greater good. And I hope that this cross-cutting theme also resonates with participants of this symposium, as it's very important that we leave no individual behind and no community behind in all that we do. So thank you for the opportunity to speak with you today. Look for the unveiling of our formal strategic research vision soon. Have a great symposium, and I look forward to hearing more about it in the coming days. Thank you very much.
Thank you, Rick. That is really appreciated. We are also looking forward to seeing the unveiling of the strategic plan for the College of Engineering. And definitely I want to point out that the desire to help society for the greater good with a focus on diversity, equity, inclusion, and climate justice is something that informs all of our research efforts. And with that, again, thank you, Rick. I'm going now to introduce Dr. Camille Crittenden, Executive Director of CITRIS and the Banatao Institute. Camille is the Executive Director of the CITRIS and Banatao Institute, but also the co-founder of the CITRIS Policy Lab and of the EDGE, Expanding Diversity and Gender Equity in Tech initiative at UC. She also served as chair of the California Blockchain Working Group in 2019-2020. Prior to coming to CITRIS in 2012, she was executive director of the Human Rights Center at Berkeley Law, where she helped to develop its program in human rights, technology, and new media. She has written and spoke widely on these topics, as well as technology applications for civic engagement, government transparency and accountability, and the digital divide. She held position as Assistant Dean for Development with the International and Area Studies at UC Berkeley, and in Development and Public Relations at University of California Press and San Francisco Opera. She earned an MA and PhD from Duke University. And with this, thank you very much, Camille, for accepting to participate in this symposium, and I'll let you speak, Martha. Thanks.
Terrific. Thank you so much, Michele, and thank you also to Olivia for managing and organizing the day so well. So I want to spend just a few minutes, and I appreciate the opportunity to speak to this distinguished group to tell you a little bit about CITRIS and our overall climate initiative, as well as some of the work that we're doing related to wildfire. So you can move to the next slide. Many of you may already be familiar with Citrus. We're one of the 4 institutes for science and innovation, and I saw one of my fellow directors, Ramesh Rao from Cal IT2, on the call today too. So we represent 4 different campuses, including Berkeley and Davis, UC Santa Cruz, and UC Merced. We were established about 20 years ago and have a really broad mandate for fostering opportunities for IT research in the interest of society, as our name suggests. So we can go to the next slide. This shows just the general map. We work at Davis not only with the main UC Davis campus, but also with UC Davis Health. We have a strong health component to our research, and we provide a number of opportunities for faculty to pursue their research, often in collaboration with each other. One of the strengths of Citrus is to bring faculty together from the 4 different campuses because we feel like this diversity of disciplines and perspectives really strengthens the output and the work that we do. You'll see the research areas here. Climate is one of the main ones, and I'll talk about that in just a moment. We also have areas in people and robots, so looking at not only robotics, but also AI and other aspects of human-computer interaction. We have a relatively recent initiative that we launched on Citrus Aviation, and that has really strong participation from all 4 Citrus campuses devoted to looking at new technologies, UAVs, as you see in the picture, but also other kinds of aviation policies that will affect and intersect with a number of the projects that you may also hear about today with respect to wildfire monitoring. We have an initiative in health, as I mentioned, and work closely with the folks at the UC Davis Health System on this, as well as in the more public health applied areas where we intersect with folks at UC Merced and elsewhere. The Citrus Policy Lab, as Michele mentioned, I was a co-founder a number of years ago, and we look closely at tech policy, both trying to inform policymakers about things that they might need to know about with respect to new and emerging technology, including blockchain, as Michele also mentioned, but then also to help technologists understand what might be the policy implications and how can we better establish ethical and responsible approaches to the technology that we develop. And then finally, the Edge in Tech initiative is around diversity. It was formerly the Women in Tech initiative, but we have broadened it more recently. And we really use this as a lens across all of the research areas, including climate, as Michele mentioned, climate justice kinds of questions. So you'll see the finer grained sort of keywords there on the right, but those are the broad research areas that Citrus works in. Next slide. So Citrus Climate, we're really delighted that Michele came on just last year, I think, as the director of Citrus Climate. If you go to the next slide, you'll see a little bit more about where this initiative has come from. Climate and environmental concerns have always been a strong part of Citrus's research footprint. We had a strong partnership with the California Institute for Energy and Environment, which is also a multi-campus research and policy center that's been working for many, many years. Before the Citrus Climate, as it's evolved now, we had initiatives on I4 energy, on sustainable infrastructures. So Michele is bringing not only the work that he's done at Davis, but really also building on many PIs and their work over the last many years. I'll talk in a minute about the seed funding program, but about a third or so of the grants that Citrus has awarded over the last 12 years have gone to climate related projects. So we have a really strong basis to move forward from. Next. And looking ahead, Michele may have a chance to talk about this a little bit more later on, but really looking at these cross-disciplinary proposals and how can Citrus be a catalyst for bringing people together to look at large-scale opportunities for research grants. Looking at how we can help UC to achieve its own carbon neutrality goals through the academic research that we bring to the table. We have a new program in workforce development, the Workforce Innovation Program, as well as a standing program through the Cal Energy Corps that helps to bring together students who are being prepared for all kinds of careers in climate-related topics, whether that's building energy efficiency or wildfire monitoring or water quality research, air quality research, all those things that we want to make sure that we're well prepared for the needs of the workforce in the future. And then finally, to look at communications and how can we expand the impact and understanding of the work that we're doing at Citrus and in Citrus Climate. Next. So I mentioned a couple of the faculty opportunities. I won't go through these in great detail because I know we want to move on to the real depth and heart of the program today. But you'll see a number of projects that we're working on that are hosted here at Citrus. I'll highlight perhaps just one. The Diversity in Tech Symposium was just 2 weeks ago or so, and that was really focused on advancing climate resilience. So those videos are available on the Citrus YouTube site, and there's a lot of wonderful content there as well. So moving on. Just to say a couple of words about our approach to wildfire. If you go to the next slide, we feel like this fits really well within the Citrus Climate Initiative and really want to bring the IT focus to the approach to wildfire. So if you think about the digital transformation of wildfire research, we're going to look at data analytics, at sensor technology and Internet of Things, machine learning, modeling, to then bring these into application areas that can really help California's response to wildfire monitoring, mitigation, and response and recovery. And of course, as California goes, so goes the world. The wildfire is not just a California issue, but throughout the US West and indeed even into Australia and other parts of the world, of course. So we want to be sure that we're helping to spread the benefits of the research internationally as well. Next. We convened a meeting in December for a special purpose, but this just gives you a sense of some of the PIs across the 4 campuses in the areas that they're working in. So we hope to have opportunities to advance their research and to further foster these kinds of collaborations. Next. I mentioned the seed funding program, and this is just a short plug for any UC faculty PIs who might be listening today. This is an annual program that Citrus runs where we offer awards of about $60,000 to a number of proposals that are collaborations between faculty members from at least 2 of the Citrus campuses. And in the past, we've always funded a number of climate-related projects, and those have been very successful. If you go to the next, I'll give you just a flavor of 2 of the more recent ones. One is around modeling for communities who need to make evacuation plans or response plans to wildfire threats. So this is one that came from PIs at Merced and at Santa Cruz, doing that kind of modeling and planning for community preparedness. And then on the right, you'll see the one also from Merced and from UC Berkeley, thinking about fire-resistant materials for buildings. And I think you'll hear more about that later on this afternoon as well. So finally, I just want to say thank you again and congratulations to Michele for pulling together a wonderful symposium. And I look forward to hearing more from the presenters. Thank you.
Thank you very much, Camille. Thank you for giving me the props, but the props really have to go to Olivia that really pulled these up together in a very, very short time and very, very professionally. With this, I'd like to just introduce very briefly again the project, give an idea of the scope and the entire research team. Due to limitation in time, not everybody that is on the research team will be able to present today. There are a lot of things that were touched upon by Dean Corsi and by Executive Director Crittenden that unfortunately will not be covered today, but there are a lot of very interesting things that are going on. Let me again introduce myself very briefly. I'm a professor of structural engineering in the UC Davis Department of Civil Environmental Engineering, co-director and co-founder of the UC Davis Climate Adaptation Research Center, and the director of the Citrus Climate Initiative for Citrus and the Banatao Institute. Next slide, please. This is the entire research team, actually not even the entire research team. These are all of the senior researchers working in the project that was funded by UCOP during the Lab Fees program of 2020. It is a multidisciplinary project that is covering really several different topics that are all necessary. They have all to be coordinated in order to really address the problem of wildfires in a way that we can provide the information for policy making and for practical solutions. The lead institution is UC Davis, but it also involves UC Merced, UC Los Angeles, UC Irvine, UC Berkeley, and two national labs, the Lawrence Livermore National Lab and the Los Alamos National Lab, as well as a non-profit research institution as the Energy Power Research Institute. I'm not going to read the name of all of the senior researchers, but let me again repeat, we span everything from wildfire modeling to air quality modeling to vegetation management to construction materials. Next slide, please. And to give an idea of the organization, the conceptual organization of this project and the vision that we have for resolving the issues of wildfires, we organize our research into 5 major research areas. WRA stands for Wildfire Research Areas. The first research area is wildfire modeling and forecast, where we approach the problem of modeling wildfires from 3 different interacting elements: modeling of vegetation and fuel, physics-based modeling at the granular scale, and the statistics-based model in order to model and forecast wildfires at a larger scale at the level of state, country, and of the order of decades in order to predict what is happening with wildfire. Then we have a wildfire research area on emission assessment and air quality assessment. Again, we need to develop emission database. We need to have a modeling of emissions, understand how the smoke is transported in the atmosphere and how that transforms into air quality. Another wildfire research area is focused on assessment of the health effect of these air quality and pollution produced by wildfires, with the characterization of the fire smoke, understanding the toxicity of the product of wildfire smoke, and then from an epidemiology point of view, understand what is the population level and the individual level health outcomes. After understanding what the problem is, we really are trying also to develop methodologies to mitigate the effect of wildfires. And we are addressing it in with 4 different approaches: vegetation management, prescribed burns, policies of land use, and the development of fireproof construction. All of these is working as a feedback loop with the wildfire modeling, because once we have mitigation strategies that is implemented, this modifies the way that wildfires will be spreading. And in order to provide this information in a way that is easily digestible and usable from a point of view of policy mitigation, we are using also scientific visualization to do that. Next slide. So there are a lot of specific scientific questions that we are trying to respond to. I'm not going to go through all of those, but just to point out some of those, there is no way yet to connect the wildfire modelings at the level of the individual building scale with the wildfire spread modeling in the WUI at larger scale. So we need to understand how to do that. there are a lot of information that are missing on what is coming out from wildfires, particularly when the fuel that is burned is coming from built environment, housing, cars, RVs, and all of these other things that are unfortunately burned down from wildfires. Again, our focus is on methodological and framework development. We are not really focused on developing a specific product, but we are developing the groundwork and the methodology to develop a different level of products that then can be used and implemented. We are focusing on California vegetation and Californian climate, and we are focusing on forecasts with a time scale that goes from days to decades. We are not yet focusing on real-time forecast in this project. And so with this, I think the next presenter is Dr. Leroy Westerling, but I'll leave it now to our moderator. I believe that Mr. Lei Zhu is our moderator. Thank you, Lei. Please take it from here.
Thank you, Professor. And good morning, I'm Lei, and I'm a PhD student in Dr. Barbardo's research group. And it's been a great honor to be the moderator for this symposium. Welcome everyone to participate in the second wildfire-induced air pollution assessment and mitigation symposium. So first, let's welcome our first presenter, Dr. Leroy Westerling. And Dr. Westerling is a professor at the University of California, Merced. His research interests include applied climatology, climate ecosystem, wildfire interactions, statistic modeling for season forecast, parallel fire reconstruction and climate change impact assessments, and resource management and policy. Today, his presentation title is Statistical Wildfire Simulations. Now, please welcome Dr. Westerling to give the presentation. Thank you.
Thank you very much. Michele, I know we're running a little bit behind. Did you want me to shorten my talk a bit, or should I take the full 30 minutes presentation?
I think the presentation is supposed to be about 25 minutes plus question and answer.
Okay.
I can recover with the break. So I don't think you need to shorten too much.
All right. I'm going to share my screen here. All right, so as Michele said, we are working on development of tools and data sets and methodologies. And my presentation today, I'm going to first give you some historical context and motivation for some of the work that I've been doing in my lab, and then talk about data sets that we have developed over the last 2 years, and then new statistical methods building on those. So a lot of what we manage in terms of climate-related risks in the past has focused on this idea of stationarity that we were able to leverage in the past. So this is showing you some typical sort of climate spaghetti, and that horizontal line is really, you know, a long-term average that we expect to return to on a regular basis. And when we have a resource that we're managing or a risk that we're managing, typically we can afford to manage for or smooth out the impacts of climate variability up to a certain point. There are going to be occasional rare events, extreme events that we can't completely mitigate against in advance. And a good example would be like a dam, right? It smooths out our water supply compared to what would otherwise be a very noisy background variability. And the problem is that our climate is no longer stationary. So in this case, that climate spaghetti I was showing you was observed and simulated temperatures for Western United States. And then, so things that are driven by or affected by climate are also no longer stationary. And that means that we need models. We need to understand what's happening to the systems, and we need to be able to model how they'll respond to future climate change, because we can't rely on past observations to tell us what's possible in the future. Well, we know that wildfire has been increasing around the Western United States, both the number of large fires in grass and shrublands, and also the area burned in those fires has been increasing decade by decade in recent years. And we've shown in the past that for forest fires anyway, it was strongly related to increases in temperature, which affect the timing of the spring snowmelt and the length of the fire season, right? You can start earlier in the season because the snow melts out sooner, and you can go later into the fall because you need more precipitation perhaps to put an end to the fire season by wetting the fuels. And so in the past, we've seen that most of the large fires around the Western United States in forest areas started in years with early spring snowmelt, and very few of the large fires started in years with late or wet spring. Well, we see the same dynamic of increasing area burned in California that we've seen more broadly around the Western United States, and not just in forest fires, but in all types of fires. And more particularly in terms of health impacts and impacts on infrastructure is that we're seeing increase in the area burned at high severity as well. So the line here is showing the number of large fires, and it hasn't changed that statistically significantly in California in recent decades. And then the bars are showing the hectares burned, and the colors there. So red is area burned at high severity. So by high severity here, we mean a lot of the biomass is consumed. And in addition, the size of the largest fire each year has been increasing. And in 2020, we had 5 large fires that, the 5 largest fires in 2020 were, 4 of them were larger than all but the largest of the preceding years. And one of them far exceeded anything that we've seen in recent history that we know of. Where's my slide not advancing? There we go. Okay. But there's another dynamic at work besides just temperature affecting fire in California, and that's increasing variability in precipitation. A warming planet changes how atmospheric circulation is organized on very large scales. And we can see that by looking at fuel moistures in different parts of California. So here, these individual lines are tracing out daily estimated 1,000-hour fuel moistures in Paradise, California, where the large Camp Fire took out most of the town back in 2018. And the decades are colored here in sequence, so you can see that as we've advanced in time, we had drier and drier conditions throughout the fire year. But look at the bolded oval there for the Camp Fire. That is an interesting anomaly, right? So we had a little bit of precipitation just before that fire, but it wasn't enough to shut down the fire season, and the fuels quickly dried out again. And we had a really anomalously dry conditions that helped fuel that fire in the season much later than we'd usually see fire in that part of the state. And that is really a function of this changing variability in precipitation. So we need the capacity to be able to understand how fire severity and fire extent have been changing in the recent past, and how it's influenced by both temperature and increasing variability in precipitation. There are products out there that describe for us fire severity, but they are not completely objective in the sense that they rely very strongly on the judgment of individual operators who are reviewing maps. And so we needed something that is consistently measured across time and across the state. And we relied on work from our colleagues, Josh Picote and Crystal Colden and others, who recently had done some work looking at how to calibrate regression models to understand how fire severity is changing across the Western United States. So we took their work in collaboration with them, refined it and implemented in Google Earth Engine, and used it to recreate fire severity maps for all of the fires in California since the Landsat record was available to do that in 1984. And so we are gathering remote sensed images, and we have implemented in Google Earth Engine a process for selecting the images and then comparing images pre and post fire to characterize the change in greenness. And then we have a nested set of regression equations in the also in Google Earth Engine, but then assign severity classes to each 30-meter pixel on a landscape within a fire perimeter. And we have applied this to historical fires in California using fire perimeters from both the Land Fire Project and from CAL FIRE. And here you can see all of the footprints of fires that we've recreated, 1,000 acres or larger in size, back to 1984. And we're currently in the process of bringing this down to about 250 to 200 hectares, depending on the data source. So it's going to be the most comprehensive record of fire severity in California that's ever been available, and it will be completely open source and transparent in terms of how the severities are derived. And that figure I showed you earlier on of the fire severity and total fire area is actually the result of this project. And we're able to do some additional analyses, of course, to understand where fire has been changing. So for example, some of the biggest increases in area burned are in forest areas within certain elevational bands. And that's helping us to understand where most of the emissions are going to be coming from as we warm up and burn more area over time. We also wanted to be able to look at daily emissions from fire. So we needed a way to get daily fire maps. So we also implemented in Google Earth Engine a fire progression tool. So we look at daily images of these fires and assign each pixel to a day burned in the fire. And then we can use that to see what severity burned on what days. And then I'm going to be showing you in a moment how we calculate emissions for those as well. So here's an example of a recent fire that we did a daily progression map for, also implemented in Google Earth Engine. Sorry, I'm losing my voice. And so we have a set of emissions factors and fuel consumption rates based on the FIN model at NCAR, working with Matt Hurteau and Christine Wiedenmeyer. And so for all of our fire perimeters and severity maps, like what you see on the left, we've been able to estimate the emissions produced for each pixel burned in each fire based on the vegetation characteristics in each 30-meter pixel, how much biomass burn based on the severity classification, and then emissions factors derived from field studies of fires in California and around the West in recent years. And just to put it in context, that bold red line in this time series is our emissions estimates, and then we've compared it to other products that we could find out there, and it seems to accord well with the available data that we have to compare it to. So we can also now look at how emissions have been changing. And in particular, you'll notice that most of our emissions from wildfires in California that impact public health around the state are coming from forest fires, and that's because that's where most of the biomass is to generate those emissions. And you'll also see that very extreme years like 2020 can account for a very large fraction of the total emissions. And we can further parse it out to understand where precisely on the map, right, that these emissions are occurring and what type of forest vegetation in particular at what elevations are driving changes in emissions in our seasons. So we now have this comprehensive record where we can understand how the seasonality of fire is changing in both its acres burned or hectares burned, and also its contributions to emissions. And in particular, we see that over the record back to 1984, a very large fraction of total emissions are driven in particular by what we call mega fires, so very large fires that far exceed the average fire size. And so a relative handful of a dozen or so of these large fires accounts for a majority of the emissions. Now, we want to be able to project into the future how fire severity, fire size, and emissions are going to change. So we have a system of statistical models that use things like climate, vegetation characteristics, and topography, and then land management and use. So what's the development footprint? What kind of fuels management are we doing on the landscape to estimate the probability of fires occurring, their size, and then their severity. We've done some of this work, and then of course their emissions. And we've done some of this work in the past for California's state climate assessments, in particular fire presence, absence, and size. And so I'm going to focus in the next few minutes just on summarizing what we're doing with fire severity modeling, because that is something of a new innovation for California. First of all, if we are able to model already, where a fire is likely to occur and how large it is, we need to know something about the fraction of fire severity in terms of how much of the total area of a fire burned is going to be in high, moderate, or low severity. So we developed a set of joint statistical models that describe the joint distribution of low, moderate, high, and other types of burn severity based on this historical record that we've created of fire severity in California. And here you can see that we do pretty well actually in being able to reproduce fire severity for, here we're showing the aggregate, but for individual fires that make up that aggregate as well. Now, we need to be able to actually map these fires at fine spatial scales, in this case, 30 meters. So I'm showing you an example here from modeling we did over northern and southern Sierra and the North Coast forests of California, but we've actually been applying this statewide, and we'll soon have that completed as well. So we actually can go in now and pick a point on the landscape. What's the probability of a fire occurring there, model the size, and then the severity fraction, and then actually simulate a fire map. So here what we're doing is a historical exercise instead, where we take fire perimeter in the location of a known fire, in this case the rim fire, and we recreate a fire severity map with our simulations. And then compare for each of the 30-meter pixels in the fire perimeter how our probabilities of different fire severity classes compare to the observations. And in this case, the lower right showing the probability burned at high severity on the vertical axis, and then the observed severity classifications on the horizontal axis. So in general, when we are predicting that a pixel is likely to be at high severity, it generally is showing up as high severity in the observations. With a simulated fire or with a recreated historical fire, there's a lot of fine detailed information in sort of local microclimate, wind, and just random chance of where embers, may end up landing and starting a new spot fire, for example, that make it difficult to exactly recreate which 30-meter pixel burn at high severity on the landscape compared to which ones could have, right? So what we really have been focused on is how can we best recreate the spatial patterning, so the type of clustering, so that our large fire, our fire severity patches have the right clumpiness on the landscape. So we use information on wind speed and direction in an iterative smoothing process. So we generate candidate high severity points, and we look at how far they are from each other and modify the probabilities of surrounding points also burning at high severity. And so we can do several iterations of that. In this case, the leftmost panel is showing the observed severity mapping for a fire in the Sierra Nevada forests. And then each of the other panels is showing iterations of this process where we first generate candidate points and then get them more and more clustered together on the landscape. And on the left now, you see examples for three different fires with multiple iterations of the clustering process. And then looking at a population of fires for the whole historical record and comparing across multiple iterations of the clustering process, we see that on average, those light pale blue dots are the ones that are closest to the 45-degree line there. In other words, it's one candidate iteration and then one smoothing and clustering iteration gets us closest to the average fire severity that we observe on the landscape in terms of how clumpy our high severity patches are. So now we have built this framework, we'll be able to estimate emissions for simulated fires by mapping them at 30 meters and then looking at the vegetation characteristics at that spatial resolution. And I'll stop here.
Oh, thanks for the fantastic presentation given by Dr. Westerling. And now it's the Q&A sessions. So before we heading for the Q&A, any questions for Dr. Westerling? Yeah. Dr. Westerling, we have a question in the Q&A sessions.
In the chat? All right,
Yeah.
Q&A. Okay, got it. How do I respond to West Coast detractors that have been saying since California stopped managing the forests around 1980, that most of the tree clearing industry has left the state? As a result, it's now cost prohibitive to remove all the dead trees as done pre-1980s at no cost to the state. And the quality of dead trees has been increasing, quantity of dead trees has been increasing and exponentially increasing fire risks every year. Well, I don't think it's true that California stopped managing forests around 1980. What is true is that the supply of old growth live trees that are very profitable to log was getting heavily restricted over time because so much of it had been logged. I think been easy for people to point their finger at regulations that came in to basically protect the last 5% or so of that kind of forest in California and other parts of the Western US, rather than acknowledge that there wouldn't have been much life left to that particular economic strategy if it had continued at the pace it was formerly being conducted at. What we see in California is that the state is putting up a lot of money for fuels management. And the federal government is starting to step up to match that. For the work I'm doing on a related project for the California Energy Commission on the Fifth State Climate Assessment, we have taken the published goals for fuels management for all of the state agencies, for private landowners, involved in commercial and forestry, and groups like public energy utilities, and translated those into fuels management scenarios, annual fuels management scenarios. If the ambition that's currently being financed across all of these groups is to treat about 1 million acres a year in California. So we've actually been mapping what 1 million acres a year of treatment would look like at 30 meters across the state annually through the latter part of the 21st century in order to map how that will affect our fire simulations under different climate scenarios. There's some more questions here. Please explain your methodology for measuring emissions. Is that ARB data? So we're not measuring emissions, we're simulating them. So that means that we're relying on field data on fuel consumption rates in different types of burns and different types of vegetation, and then estimates of what the emissions are. And that's based on field observations and laboratory observations. So these are parameterized process-based models for estimating the emissions. Another one, can we assess the emissions from houses burning in wildfires? And if so, how do they compare with those from forests or other biomass sources? So basically, we're having to treat houses as a new fuel type. We don't currently have that parameterized into our emissions model, but I have colleagues working with me on another grant who are doing that. We don't have the numbers yet because of the delays from COVID. They've been building large-scale facilities for burning things and estimating the emissions from them. So, what is the accounting for the more recent forest fires compared to the previous years? I'm not sure how to answer that question. If somebody wants to clarify, I could. Okay. Are there any other questions or?
Okay, so thanks again for the fantastic presentation, Dr. Westerling. Like due to the time limits, if your question remains unsolved or like you want to discuss more question with Dr. Westerling, feel free to do it like later on, contact him or like contact the research group. And let's thank Dr. Westerling again for his fantastic presentations. Now let's welcome our next presenter, Dr. Matthew Moody. Matthew is currently working on a fast response environmental model, which dynamically link atmosphere winds and fire-induced winds for use in wildfire spread models. Matthew completed his PhD in mechanical engineering at University of Utah and is currently a postdoctoral scholar in mechanical engineering at UC Davis. working with Professor Brian Barley. Prior to receiving his PhD, Matthew worked in the oil, gas, and chemical treatment industry with 17 years experience as a design engineer for fluid measurement system. Today, his presentation topic is adaptation of a dynamically couple-fired spread model to account for the heterogeneous terrain and fields. Matthew, please share your screen and start your presentation when you're ready. Thank you.
Yeah, thank you for the introduction. So one of the things that I've been looking at is how we dynamically couple the winds to the fire front. Specifically, winds are one of the major drivers of the fire spread right at the fire front. And how do those winds interact with the fire, and how does the fire affect the winds at the very fine scales, roughly the scales of 5 meters down to a meter even. And particularly, how do we start to account for the changing wind conditions in heterogeneous terrain, something like mountain canyons or in the wildland urban interface when we have buildings in it? There we go. And when we start talking about wildfire modeling, there's a lot of different models that are out there. There's things that are, say, something like WRF-S fire, which takes meteorological conditions and brings them down into the fire scale and tries to solve the momentum and the energy balances, but can only do it at very coarse resolution. On the other end of the spectrum, you have something like, say, the wildfire dynamic simulator, which is very fine simulation and solves things such as combustion physics, but the resolution needed to do that requires that the domains be very, very small. So it can only it can only spread wildfires in a very small area, something around 1 kilometer or so. And then we have empirical models like Farsight or Spark, and there's multiple others out there that just parameterize the different areas of fire. Now, anytime we talk about wildfire modeling, in some instance, all of it is parameterized. Again, if we were to, say, solve all of the physics and chemistry involved in combustion of wildfires and how they spread, even on supercomputers, we could maybe simulate the burning of a log. And so we're always trying to add some empiricism into these wildfire models. Anytime we talk about modeling, especially numerically modeling, there's a trade-off between the accuracy of our models and the speed of our models. So if we include a lot of accuracy and we include all of our physics, then our speed begins to slow down from a computational standpoint. Whereas if we parameterize and we use a lot of empiricism, our accuracy goes down, but our speed goes way up. And so it's always a balancing act of what's most important. Now, the tool that we've been developing is based on the Quick Environmental Simulations suite. And the Quick Environmental Simulations is a series of modules that all interact with each other. We have a turbulence model, we have a wind solver, we have a scalar transport model and a radiation model. The two that I'm really going to talk about today are the QES winds and the QES fire. And QES winds, and as we step through QES fire, this is an overview of how the system works. So it begins and it initializes our fire map and our ignition sources and our fuel sources in the domain. QES winds then calculates an initial velocity field. Then for each cell that's on fire in our domain, QES fire calculates the rate of spread for that, as well as the heat release from the fire. It then calculates our plume velocities from that to couple that to the winds in the atmosphere and give the feedback for the rate of spread and the heat release. And then we begin to merge these plumes as we go up in our domain. So we'll merge our plumes together and calculate what those velocities are. And then that's superimposed back onto the initial velocity of the winds. And this is where we can dynamically couple and have the winds affect the rate of spread, but also have the heat release from the fire affect the winds. We then run our wind solver one more time to calculate our final velocity. And if it's converged, then we move on to our next time step. If it hasn't, we run the loop one more time to try and converge that. Now, the heart of QES simulation is the QES wind solver. And the QAS wind solver is a mass consistent diagnostic wind solver, which means that we're only enforcing conservation of mass. So anytime we have something like momentum or energy budgets or anything that has to do with conservation, those other conservation laws, they have to be parameterized. We have to put something in their form. And the way that QES winds work is we would take an initial wind field that's something like this. So this would be a wind field over a flat ground, where next to the ground we enforce our no slip condition, where and then going up to the atmospheric winds as we go up in the domain. So again, anytime we're going to have something that's a momentum or an energy deficit, we have to parameterize that. So QAS winds was originally developed to run in urban corridors. And so a lot of these slides coming up are going to be about buildings. Now, for instance, here, the green background
this is Michele. Sorry to interrupt you. But right now, the attendees are seeing your image and not the one of your presentation.
Let me see if I can, okay. Can you see my slides now?
Yes.
Okay. Okay. Sorry, so if we look back at this, so our, again, QES winds, and if I go back here, let me just go back to this slide. So here we would look at a wind profile across flat ground, where again, at the very bottom of the ground, we have a very low velocity. And as we go up in the domain, our velocity increases to what our free stream velocity would be at the top. So again, if we're going to parameterize around the momentum sinks, or energy sinks, such as a building, we have to parameterize that. So here we're looking at, in figure A, is the blue block is a building inside the domain. And upstream of that building is, in the red that you can see, is our upstream parameterizations, which just says that we know that the wind has to slow down due to the momentum sink of the building. And so we superimpose a velocity there that gives us something that would cause that to happen. We then run our mass consistent, we then solve for conservation of mass, and in B we get what that, so in B we get our superimposed velocities, and then after we run our conservation of mass, we get something that appears like what we see in real world parameter, or in real world conditions, such as we see a recirculation zone around the front of the building here. And this has been very well studied, again, especially in urban areas. We can also apply this in different parts of the domain. So here we're looking at the downstream of a building, where the blue again is our solid building. The yellow area in the top left figure is our wake zone, and then the red area is our wake recovery zone. So then if we look at the top right, this is where we impose those velocities. And then the bottom is, again, after we run our mass consistency, we get the recirculation zone behind a building that we would expect to see. This has also been done for street canyons. We can look at, say, 2 buildings here. Now, this becomes important later on because we need to decide, one of the ongoing research areas in these mass consistent solvers is what parameterizations are most important. For example, the momentum deficit of a very large building should be much more important than the momentum deficit of a smaller building. And so here we see that we have the recirculation zone, that the smaller building is actually fully in the recirculation zone, and then we parameterize in a street canyon in there. This has also been developed. We have parameterizations for things such as a single tree. This was, and then we can put and take all of these parameterizations together, and we can get velocity fields in very complex domains. And again, because we're only solving for the conservation of mass, these solvers are incredibly fast. QAS winds can solve a domain that, if we were to do it in direct numerical simulations, we are about 7 to 8 orders of magnitude faster than those simulations. So when we start talking about fires, we need to now parameterize what our fire domains are, and what the winds are from the fire. Now, we do this in QES Fire using the Bauman-McCaffrey plume rise model, which basically gives us, if we know what the heat source is, it gives us a characteristic length and a characteristic velocity and tells us where those velocities occur and what the velocities are. But again, we need to know what the characteristic heat is. And so we've also taken the empirical temperature profile and velocity profile based on McCaffrey's work back in 1983. And we can, and again, this is where our empiricism come in, where we can say, all right, we know roughly what the heat release is for a given area and for a given fuel, and therefore we can calculate out what the vertical velocity and the temperature profile inside that is. Now, if we marry these two together, we can actually get and calculate out what our potential velocity field would be. And we get a plume rise model that we can now superimpose into our velocity field in QES winds. And it gives us something that looks very close to what we see in real conditions. And the advantage that we have in the methodologies that we've chosen is that we can do this for each point in the domain independently, which means that we can run the calculations in parallel, and then they can all be superimposed together. And this has been shown to work very well in real world applications as well. The problem arises when plumes begin to merge together. So we can superimpose everything as long as the fires are distinct, or as long as our fire lines are distinct. But as they begin to merge, we have to account for that somehow. And so what we've done is we've taken some work that was done back in the early 90s on merging axisymmetric plumes, late 90s, early 2000s, on axisymmetric plumes and how they merge. And what was typically done before this was that we would say that these plumes merged when they interact with each other, when they overlap with each other. And instead, Kay and Linden said, no, they should merge when there's no longer a difference in the buoyancy, in the maximum buoyancy flux between these plumes. And so we've taken that and we've said, okay, we can calculate out what our merging height is. And this is a function of the radius of the plumes and the distance between those plumes. Now, the radius of the plumes we're getting from our empirical models that based on the heat release of it, and the distance between these plumes we can calculate very easily inside of QES Fire. We can then calculate a virtual origin for these two merged plumes, and we have now a plume above it. And so what we would do is we would take from the ground level, which is where you see the first dash, the bottom dashed line is our ground level, and the white, red, red, white would be our cells that are on fire, our cells. So our red cells are on fire. We can take those two plumes and we can consider them distinct and superimpose them on our background velocity field up to that calculated merging height that we have. Now, above that merging height, we calculate a virtual origin, and we then calculate the velocity field from that merged plume above our first merging height. Now, we can do this throughout the domain as we go up in our domain height to rapidly calculate what the fire-induced winds are for the entire domain. So from here, from ground level 0 up to our first mixing height, zeta 1, we have 7 distinct plumes. And then from zeta 1 to zeta 2, we begin to merge those plumes together. From zeta 2 to zeta 3, we merge them again. And we continue this all the way up until either we've merged all plumes or we've reached the top of our domain. And this is a schematic of how this works. If we look at figure B here would be our horizontal domain, where the dark gray are burned out areas, and the dark red areas, or the dark red cells, are cells that are on fire. And A is actually the vertical velocity contours from the merging plumes as we go up. And if we look at the very lowest level, we can see that those plumes are considered distinct, but as they go up in height, they begin to merge together. Now, the question is what happens when we have unequal plumes? Now, those plumes can be unequal from several different reasons. One, they could be different because of the terrain. If we have slopes, obviously the heat release is going to be different at different vertical levels based on how close they are. For example, at the very bottom of this slope, the heat release is going to be much different higher up at a vertical level than one at the top of this hill. We can also have differences from the fuel type. Now here, so what we've done is we've said, okay, well, we can match these plumes, and again, now we need to have some way to calculate when these plumes will merge. Well, we can do that through the buoyancy flux. And so what we do is we calculate the buoyancy flux, and again, we do this based on our empirical knowledge of what the fires look like. And we calculate the buoyancy flux at a given level. So we would take the highest elevation, and we would calculate the buoyancy flux at that level for all plumes that are being merged up there. We can then displace that plume up to that vertical level based on the buoyancy flux and recalculate its new plume parameterizations, and then merge them together. So here we would, again, this is the sort of the final picture of how this would look, but at the vertical, at the horizontal, or at the ground level, we run our plumes from ground level up to that merging height. And then we again calculate a virtual origin above that merging height, and we do this, and we have our plume and our velocities coming in. And we've recently modeled this with a prescribed burn in forested, heterogeneous terrain, heterogeneous fuels area at a burn in Florida back in 2012. And this was a well-documented, well-instrumented burn. So we were able to look at the spread rate of the fire as well as the velocities inside of it. So here's an overview of what the fire was. Again, this was Eglin Air Force Base in Florida back in 2012. And this is an overview of how this looked. Now, this fire was started with 3 distinct lines. We have the red line at the top, the purple line running through the middle, and then along the road at the very bottom of our domain here, we have another ignition line. And the ignition was started by 3 ATVs that were had GPS on them as well. And so we were able to know exactly what the ignition lines were for these. And for comparison later on, there's a meteorological tower at the shown in the domain here, which is where we're going to be comparing the wind speeds to. So what we have is we have our simulated burn of this, where this is the terrain as we go through, and the red lines are our fire line as it progresses through, and the black is the burned out regions. And the way that the model works is that we match our ignition times, but after the ignition times are matched, we just let the fire burn through. And what we found was that we were actually able to match the area burned as well as the velocities inside the fire line as it matched very well. And again, what's most important for us here is trying to get those velocities correct as the main driver for a fire line in a wind-driven fire. So again, and here I show the meteorological tower as the white triangle in the center of the burn for how we compare the winds. And what we can see is here, the light gray lines are the, in panel A, are the observed wind speeds at the meteorological tower. The thick black line is the wind speed modeled by QES Fire. Now in panel B, we have the temperature at the meteorological tower as well. And we can see that there are 3 distinct peaks in the temperature as it moves past. Now, this is due to the fire front moving past at different areas of it. But what we notice is that we see the spike in vertical velocity as in both the measured data as well as the simulated data in our model. And it matches up really quite well, and it matches with when the fire fronts pass through the meteorological tower. And previously, we were looking at a height of 3 meters. This is the same tower data at a height of 9 meters, roughly. And again, we see the exact same trends that move through. And so our model is performing fairly well there. Now, again, anytime we have to talk about QES Fire and our parameterizations, we now need to start talking about how our parameterizations overlap. For example, if we have a large building and a small building, we know that the large building will be dominant. Well, what's the more dominant parameterization in this area? In this instance here, we would say that possibly the fire is the more dominant parameterization. Whereas if we look at, say, this scenario, possibly the building is going to be the more dominant parameterization that we need to look at. And then here we could say somewhere in between, right? We have a fire line moving down into an urban area, but how do we, which is going to be more important in terms of the parameterizations, the fire or the buildings, because we have to choose one or the other to put in. And so again, if we just look at a brief schematic, and this is work that we are currently doing right now, and trying to determine if there's a way that we can calculate the importance of the parameterizations in the wildland urban interface, we can look and we can say have a building of a certain height and a fire of a certain height with an incoming velocity profile. And that, again, that velocity profile would be driven by what our winds are in the area. Now, in this case, we might get something where the streamlines would, the fire would force the streamlines up and over the building, and then we would get a recirculation zone around the building. But what happens if a fire is very close to the building? Would we expect that same recirculation zone behind it? Would the building now slow the fire down enough that, or slow the winds down enough that it changes the driving force on the fire? Or if it's very far away or very low wind speed, here we have a very low wind speed, possibly our streamlines just go vertically as we hit as the fire forces, the buoyancy forces up. Or if we have a very strong wind and a very short building, possibly, again, the velocity overrides and the fire overrides what the building parameterizations would be. And what we're really talking about in these parameterizations are the forces of the buoyancy from the fire and the fire-induced winds from the heat release of the fire, and the momentum coming from winds or buildings or trees. Again, we can get better models with trees as we put in a forested area into these models. And so we're really talking about the ratio of these buoyancy to the shear forces in our parameterizations. Well, this is by definition the Richardson number. And so we can take the Richardson number as the ratio of the Grashof number and the Reynolds number, which is, again, just the buoyancy forces over the shear forces in our flows. And if we calculate these out, we can say that if our Richardson number is very, very small, we can ignore the free convection. In other words, we can say that if our Richardson number is very small, effectively, shear forces are going to dominate. And if our Richardson number is very large, then our buoyancy forces are going to dominate. And if it's somewhere in between, then we need to account for both of those. But this at least gives us some way that we can rapidly calculate which parameterizations begin to override inside the wildland urban interface, which gives us a way to now move our QES fire into that regime. Now we've done this, basically this is our first pass at putting these together. And what we have is we have two buildings, which are the solid blue blocks in this. The solid red block on the left-hand side is our fire, and the arrows are our velocity contours as we move through this. So we can see that as flow is moving from left to right, the fire forces the velocity vertically as we begin to have our plume entrainment and our buoyancy forces from the fire itself. And we still see the recirculation zones behind the buildings that we would expect to see. And again, this is a very preliminary data. We haven't tested this in a lot of different cases yet. That's where we're going to next. But we believe that we now have a methodology that is pretty sound to apply our parameterizations and how to do that. And with that, thank you.
Thank you, Matthew. And thank you, Matthew, for his fantastic presentations. And let's move to our Q&A sessions. So we have our question is like, how are you treating building leeward turbulent wake regions in your modeling?
So one of the, when we talk about a mass consistent solver, such as QES winds, we are never solving turbulence. And so how we're solving the leeward turbulent wake regions is they're just parameterized as a quasi steady state. So because of that, we're not, and again, this is because we're not solving momentum or energy transfer. We're not solving any of the turbulence models. So it's just parameterized. And this has been really well studied, and it's based on work done by Rockley. It's the same methodology that mass consistent wind solver like Quick uses. In fact, Quick and QES are very, very similar in the way that they handle those building parameterizations. But I guess the short answer is we don't treat the turbulent wake regions. We just parameterize those turbulent wake regions based on data that we get from wind tunnels and field experiments.
Okay, thank you. So our next question is, how does QES winds compare to other models like Wind Ninja?
It compares well with other models like Wind Ninja. The Wind Ninja is another mass consistent wind solver. There are differences. Wind Ninja is a terrain following coordinate system, I believe, and QES Fire is not. So we just have an Eulerian framework, and we don't change our ground level based on terrain, whereas Wind Ninja does. But it's very similar to something like Wind Ninja.
Okay, thank you. So our kind of last question is, have you thought about modeling verification near fires with 3D wind profilers for both horizontal and vertical wind field measurements?
So we have, and I, just in the interest of time, I didn't go through the full validation that we did on QES Fire. As part of this project, we actually have published our first paper on this, but we did look at the model verification using WRF S-Fire, and which is a large eddy simulation mode, and I believe, yeah, they ran it in large eddy simulation modes, and we were able to show the differences between QES Fire's wind profiles and the profiles of WRF S-Fire that were done using conservation of momentum and energy, and there were distinct differences and similarities between them. Again, this is one of those, WRF S-Fire definitely did a better job of it, but it was also much longer time to calculate it. For example, the same simulation took 3 hours to run on WRF, and we ran it in 12 seconds with QES Fire. So again, it's that trade-off between speed and accuracy.
Okay, thank you. So another question raised out is that how do you parameterize building in modeling wildfire spread? Can you predict what buildings will burn?
So at this point, we can't. That's definitely something that is a future project to put into QES Fire. At this point, we are really just trying to understand what the winds do around the buildings with wildfires as they approach them. We would need another model in terms of how predicting which buildings will burn and won't burn, but we can't really get those models in there until we really understand how the winds are affected by both the buildings and the fire.
Okay, thank you very much, Matthew, and thanks again for your fantastic presentations.
Thank you.
Next here is a 15 minutes break sessions. So let's take a break, and Dr. Bobardo, do you want to move the break a little bit longer, or like do you still? Welcome back, and here is the second wildfire-induced air pollution assessment and mitigation symposium. And our next presenter is Dr. Catherine Collin with her PhD candidate, Caitlin Jones. Dr. Catherine Collin is a co-director of the UC Davis Climate Adapters Research Center and an assistant professor jointly appointed in the School of Medicine Department of Public Health Sciences and School of Veterinary Medical Department of Medicine and Epidemiology. Her research focuses on the characterization how climate change influences humans, animals, and environmental health. She employs environmental epidemiology study designs, utilizing spatial temporal exposure assessment and weather, climate, and land use model outputs. She also used mixed method for social and behavioral epidemiology. She worked with state and local health practitioners to systematically characterize the implement climate change and public health action in support of building and evidence based on climate change and health interventions. And his co-presenter, Caitlin Jones, is a doctoral candidate at UC Davis in the graduate group in public health science, working with Dr. Catherine Collin. He currently focused on the relations of environmental health hardware, economy, integrity, and public health. Prior to joining UC Davis, Caitlin completed her master at Tufts University Cummings School of Veterinary Medicine, followed by the CAL-EIS fellowship with the California Department of Public Health. In her fellowship, Caitlin published findings on the association of wildfire smoke and cardiovascular health. So let's welcome them to give the presentation, which the title is Developing Exposure Risk Profile for Populations Experiencing Wildfire Smoke. Thank you very much and welcome.
Thank you for the introduction. So Katie will be sharing screen, and I'll go ahead and actually start with the presentation.
Yeah, I just want to double check that the audience is seeing the presenter mode and not like the notes slides.
Yes.
Yep.
Okay, so I'll go ahead and get started. So yeah, our presentation is talking about developing exposure risk profiles to look at populations experiencing wildfire smoke exposures. Next slide. So I'll start by talking about why we wanted to develop these exposure risk profiles. And this project we've split into 2 phases. So then I'll talk through the first phase, which is developing the profiles and looking at indicators of risk. And then that's where we're currently doing our work. And then I'll talk about phase 2, which is sort of our next planned steps in taking this data and linking it with health outcomes for an epidemiologic analysis. And at the end, Katie will talk about a current project that she has coming out under review. Next slide. So when we think about exposure to wildfire smoke, we know that there are differential health effects, and these potential impacts can relate both to sensitivity and exposure, as we see framed here in this vulnerability framework. And when we think about these characteristics that have been studied in epidemiologic evidence, we often look at the sensitivity to the impacts of exposure. For instance, age, which can relate to these underlying risk factors that increase our risk of experiencing an adverse health outcome. But we also have the exposure side of this equation to think about. And so that's where we're sort of focusing in on the work, is what characteristics specifically relate to risk of exposures and how do those differ across populations? And trying to understand these differences across population characteristics for exposure risk can help improve our exposure assessments, because we're often looking from an aerial perspective of exposure and not really understanding the true exposure that individuals are experiencing, which could be different based on the risk reduction behaviors or adaptations that are available to them. And so trying to think about those characteristics of the environment, their place, and what resources they have available to them that can increase or reduce their risks of experiencing exposure to wildfire smoke. And then estimating the population level changes in disease burden attributed to wildfire smoke exposures when considering how it relates to that risk of exposure. Next slide. So within this project, as I mentioned, it's 2 phases. In the first phase, we are aiming to construct these place-based population exposure profiles representing common populations that are at risk of exposure to wildfire smoke in California. And these profiles will contain information on environmental, demographic, socioeconomic, health status, and housing risk factors, which will be derived from literature and expert knowledge on the relationships with smoke events. And then in our second phase of this project, we aim to link these exposure risk profiles developed from phase 1 with hospitalization and emergency department data to estimate disease burdens during wildfire smoke events. And so we'll utilize some of the wildfire smoke products developed by our other collaborators on these projects. And then our objective is to really determine how well the exposure risk profiles are able to predict these adverse health outcomes. Next slide. So I'll start by talking through phase 1, which is developing the exposure risk profiles. Next slide. So as I mentioned, we started doing this by reviewing literature on these specific risk factors that relate to wildfire smoke experiences at a community or population level. And we're also incorporating our expert knowledge on what we know to be the relationships with wildfire smoke events. And from doing so, we identify measurable indicators of risk and then descriptively map those to try to understand how they're distributed across populations, and to then identify and define census tract level risks that represent higher risk populations within these different regions. Next slide. So from the literature, we identified these 4 risk categories. And we think about home environment as an indicator of how individuals may experience or be exposed to wildfire smoke in their home due to outdoor air infiltration. And so we think about how poor housing qualities can increase risks of exposure, while we can also utilize adaptations like heating, ventilation, and air conditioning systems to reduce our exposures within the home environment. And so as I talk through these risk categories later on, I'll talk about which specific measures and indicators we'll use to further define those. So in addition to the home environment, we're also looking at the outdoor environment and which characteristics related to qualities of environmental health can also confer protection or increase risk for wildfire smoke exposures. And then risk behaviors, we think about how individuals can reduce exposures through behavioral adaptations, such as staying indoors or reducing outdoor physical activities during smoke events. But sometimes there are demographic, socioeconomic, occupational, other factors that may actually dictate or influence those risk behaviors. And so we're looking at those specific factors that may indicate which type of behavioral adaptations an individual or a population group is making. And the last risk category is adaptive capacity. So this is the ability to reduce exposures, which encompasses capacity of individuals, communities, or systems to respond to environmental change, such as wildfire smoke. And this relates to vulnerability and resiliency at different levels. And so it can be difficult to assess. But in relationship to wildfire smoke, there may be key factors which broadly infer adaptive capacity of an individual or community, such as socioeconomic and demographic factors. And so we're looking at these key indicators that may dictate access or availability of these resources within a population group. Next slide. As I mentioned, we're really interested in identifying measurable and actionable indicators that are accessible for local public health operations. And so we're looking at these publicly available data sources from Census, CDPH, the California Energy Commission, and CAL FIRE to try to identify indicators for each of these risk categories at a community level. And then later on, we'll take those exposure profiles from community level and link it to individual level data from health outcomes in order to examine the impacts on health related to these exposure risks. Next slide. And so using these community level measures, we're looking at mapping them descriptively to identify the range of values in the distribution of the higher risk values within those populations, and then to identify a community level indicator of risk based on each variable that we're looking at. And we've done this for the Sacramento region, and this is really just a proof of concept because ultimately the study regions for this project will be in other parts of California. Next slide. So now I'll sort of talk through the different indicators that we're looking at for each of these risk categories and sort of how we're defining our higher risk groups within each of those definitions. So for the home environment, we're looking to acquire data on air conditioning use from the California Energy Commission to look at the ability to reduce that exposure to wildfire smoke in the home environment. But we're also looking at physical characteristics of housing, such as housing age. There's prior research showing that housing built before 1960 has increased risk of outdoor air infiltration relative to homes built after 2000. And so we're looking specifically at the year built to try to identify those that have a higher risk of outdoor air infiltration in the home. And also thinking about housing qualities, we're looking at low-income housing using the HUD definition of low income, which is households that are earning 80% or less of the median income for that region. And so both of those indicators may ultimately be combined to look specifically at older low-income housing as the higher risk group for the home environment. Next slide. And then thinking about outdoor environment, we're talking more broadly about the environmental qualities that may relate to our risks of exposure. And for this, we're drawing upon what we know from ambient air pollution literature, in that tree canopy can help absorb and reduce ambient air pollutants. And so we expect that there would be a similar relationship with the air pollutants from wildfire smoke as well. And so we look at how regions that have less tree canopy may experience a higher risk of exposure due to those qualities of the environment. Next slide. And now talking about risk behavior. And so, as I mentioned, this is sort of individual behavioral adaptations that may be taken in order to reduce your risk of exposure, such as staying indoors or reducing outdoor physical activity. But sometimes there are certain characteristics that may dictate which risk behaviors we take, such as our commute to work or the occupational industry in which we work. So in thinking about both of those, we're looking at those who are commuting outdoors via walking or biking as a higher risk group, or outdoor workers in agriculture, forestry, fishing, hunting, mining, and construction. And then we also know that there are sex differences in epidemiologic evidence associated with wildfire smoke exposures. And there are some studies showing that women are more likely to adhere to air quality warning systems. And so these differential health effects may be more than just a difference in biologic susceptibility, but rather differences in our risk behaviors as well. Next slide. So lastly, within the risk categories, we're talking about adaptive capacity. And as I mentioned earlier, this is sort of more of a broad encompassing term to look at our access to risk information, as well as adaptive resources. And so we look at income as a reflection of individuals' ability to mitigate exposures through access to clean air or your ability to evacuate and relocate during these wildfire smoke periods. And we also know education can be a proxy for socioeconomic status in a similar way to indicate that capacity to mitigate exposures. But we also know there's a relationship between education and poor health outcomes that can be partially explained by reduced health literacy. And so low education may also relate to reduced adherence to risk communication. And in thinking about the primary language spoken at home, this is important in the access to risk information, which is important in our adoption of health behaviors and individual level adaptation strategies. And then lastly, we look at race ethnicity, which we know has been shown to have disproportionate exposures to wildfire smoke by race and ethnicity, but this indicator doesn't necessarily reflect cultural or social differences, but actually may be a poor proxy of structural disadvantages. And so what we'll be investigating is how we can combine this indicator with other socioeconomic measures in order to better understand those structural disadvantages that relate to risk of exposures to wildfire smoke. Next slide. So in talking about each of those indicators, we want to think about, I mentioned how we're characterizing higher risk, but how do we do that at a community level? And so there's sort of two approaches we've taken to this. Next slide. The first is to look within a single census tract at the proportion of the higher risk population within that census tract. And so where there is a majority, 50% or larger of a higher risk value within that census tract, then it will be assigned that definition of high risk exposure for that indicator. Next slide. The other way we're conceptualizing this is to look at the distribution of the proportions of the higher risk population across the census tracts within our defined region. And this is to try to understand the variables like commute to work or occupational industry, in which the higher risk values will always be a smaller proportion of the overall population for an individual census tract. And so we just want to capture census tracts that have the higher values of those proportions. So looking at the 50th percentile for the proportion of the higher risk population across all the census tracts for that region, and just defining those census tracts as a higher risk of exposure. Next slide. And so that brings us to the next step. So as we're sort of defining each of these variables for the exposure risks for each indicator, we'll be mapping those. And you can see on the right side there, the Sacramento region mapping the higher risk for housing age. And so for this indicator specifically, we looked at census tracts where 50% or more of the occupied housing units were built in 1960 or earlier. And we defined that as a higher risk housing. And as we construct this risk matrix to classify vulnerable populations, we'll try to identify ways in which we can merge these variables, as I mentioned, looking at older and low-income housing census tracts and looking at the potential for redundancy among these variables as well. And then our next step will be examine the intersections of exposure risk profiles with wildfire smoke exposure data that we're getting from our collaborators on these other projects. And so that brings me to phase 2. And this is what we'll do ultimately next, is linking that health data to these exposure risk profiles. And so for this, we're looking at cases of respiratory, cardiovascular, and cerebrovascular morbidities. And these are outcomes that are commonly associated with wildfire smoke exposures. And the aim of this is to try to better understand how those are differentiated by the risk of exposure to wildfire smoke. And we're specifically acquiring hospitalization and ED data from HCI. This is on a trajectory to become a statewide PAIRS database within the next year. Right now, it currently captures the majority of healthcare facilities within California, with roughly 8,000 facilities. And we anticipate getting this data in summer 2022. So we'll start linking that to our community level exposure risk profiles and that wildfire smoke exposure data within the next year to look at how these health outcomes vary. Next slide. We do anticipate that we'll see higher risks of exposure to wildfire smoke result in increased vulnerability to adverse health outcomes. But we also expect that this relationship may be modified by factors such as age, which we know that interventions and guidance for wildfire smoke does not advise the same interventions for young children, such as N95 masks. And so there may be certain age differences in risks of exposures, in addition to differences in risk behaviors between younger adults and older adults. And so this may be something important to look at. Urbanicity as well may relate to differences in some of the factors we're looking at, such as tree canopy, which in urban areas can be protective by reducing outdoor air pollutants. But when looking in these rural areas or high fire risk regions, tree canopy may relate more to the risks of a wildfire event and subsequent smoke exposure. And so that's something we'll look for as we start linking this with our health data to understand how different population subgroups may differ. Proximity to high fire risk landscapes is another thing that we'll sort of look at to see how these risk profiles differ across these different groups. And with that, I think I'll actually hand it off to Katie now to talk about her project.
Great, thanks. So we're going to be transitioning to a bit of a different topic, but it's relatively related. It's an important analysis that was led by Dr. Eric Chu, who has extensive policy experience. But what we were mostly interested is really thinking about what the institutional drivers are in regards to planning for cascading disaster risk. So as we're talking about wildfires, we are inherently talking about the smoke, especially from a public health perspective, we're thinking about what smoke does to health. And in most cases, when wildfire happens, we do see that it can co-occur with other hazards like air pollution that already exists, extreme heat events. And so what we really wanted to do was take a look at the state of California and counties at the county level, some of the plans, the formal plans that are written out to address cascading risk at local governments. And so there's very little data that actually provides any information about what level of planning is being done at the local level for cascading disaster risks. As we know in California, there's all sorts of examples of what this can look like, whether it's drought occurring at the same time as extreme heat happening at the same time as wildfire events. These are simultaneously happening events, so it can be a bit challenging.
Sorry, this is Michele. I want to tell you that it's switched to your image, not to the slides. So can you pause and reshare your share screen?
Yeah, hold on 1 second. See. Is it working now?
Yep. It went back to you now.
I just want to double check. For some reason, I'm not able to see my, hold on 1 second. Let's try this again. I think the problem is that I have dual monitors. Is it still doing it?
No, now it's fine. Now it's back on.
Okay. Strange, sorry.
No problem. Thank
some
you.
of my notes. Okay, so for this project, what our goal was is to assess the knowledge on institutional approaches for addressing wildfire-induced air pollution in California. And so what we did was a qualitative document analysis of county level different types of plans. And our selection criteria was that we wanted to find relatively recent publications, and by relatively recent, we mean since about 2005, of either local, they had to have a local hazard mitigation plan and either a community wildfire protection plan or an air quality hazard mitigation plan. We were also looking at counties that had well-defined or established exposure to both wildfire impacts and poor air quality, since we're interested in that cascading disaster risk. So we identified those counties by looking at some of the tools that are available from CAL FIRE and OEHA CAL EnviroScreen specifically. And we also really wanted to prioritize those counties that had very clear intentional engagements around wildfire, smoke, and climate change, and air quality specifically. And so what we did was we ranked the local hazard mitigation plans according to some terminology that we identified to capture themes around wildfire, air quality, and climate change. And we also focused some of our content analysis to really try to understand some of those socioeconomic vulnerabilities that are being considered in those plans, as well as the policy and institutional responses and the processes for planning and acquiring resources for these plans. So we ended up with 22 counties across the state. You can see that there's a variety of different types of plans that they have. They all have some local hazard mitigation plan, as was required by the selection criteria, and some combination of either a community wildfire protection plan or an air quality plan. You'll see the spatial distribution is pretty much across the state. So we have counties in Northern California, in Central California and the Sacramento Valley and along the Bay, and then in more Southern California where we see fires across the state. And so there are really four main areas where we have our major results. And the first is around data and information. So the state of California itself has an abundant scientific capacity to be able to assess hazard impacts, to model future hazard trends. We're seeing some of this in the presentations that you'll see across today, and abilities to calculate human risks, asset risks, and also look at different types of vulnerabilities across regional, local, social, ecological scale. So there's a ton of data that's available. And you can see on the right in this table that there is a list of some of the actual tools that we found that were referenced as data. We do note that the CAL FIRE's fire hazard severity zones is most frequently cited and used in a lot of these plans. And in some of the plans, we do see that very specific local geographic and ecological features frame how they think about wildfire vulnerability. And we identify future opportunities within this, within each of our concepts here, and specifically for data and information. There's not a lot of established criteria for metrics to monitor and evaluate how that data is being used, or even how it can help inform planning. And so we think that there's a lot of opportunity there in itself, so that there is less of an institutional gap between using these tools to identify areas where there may be some wildfire risk, but actually translating that into actionable items so that they can be used to develop interventions or certain policy plans that can then be implemented. So there's a lot of data that's available, but that how that's translated into implementation has yet to be seen, specifically for cascading risks. So these risks that happen in sequence. So our second theme that we found results in is in this regulatory context. And most counties follow both the FEMA and the CAL Office of Emergency Services regulations that for planning for these disaster events. So they're kind of prescripted, and they act as a living document, meaning they can be updated regularly or not as regularly, but they oftentimes require technical consultation. So a lot of times we found that counties would subcontract out for technical information to be included in the hazard mitigation plan. And so where we see an opportunity for growth there is to institutionalize some of that knowledge, some of that technical skill into the already existing workforce, so that those who are doing the planning or implementing the planning moving forward don't have to rely on an outside source to know how they'll be able to adapt fairly quickly to these changing events. And so the third area of results that we found is thinking about the planning process. So similarly to what we saw in the regulatory process, a lot of the planning is kind of led with external consultants. It can incorporate a wide range of local and regional participants, but most of the actual planning is done using tools that are established from the Disaster Management Act, which is from 2000, and is really relies heavily on that technical expertise. In order for a planning process or a plan to actually be certified or considered official, it has to meet certain FEMA requirements. And this is really important. So for communities that are planning to have to apply for FEMA grants or any type of FEMA funds, especially after a disaster, then the plan often has to account for each of the important steps that is established in the FEMA requirements for disaster plans. So that kind of limits what counties are able to do in terms of their creativity for thinking about these more dynamic and complex hazards that aren't just singular but actually are feeding across each other, as we see with wildfire smoke and air pollution events. And lastly, funding and resources. So many of these jurisdictions, as I've mentioned, do rely on FEMA funding so that they can get support to do their disaster planning. So as I said, they're kind of siloed to have to think about how they're going to answer the FEMA call with their plans, specifically addressing the content that they require. Oftentimes, this can be supplemented with in-kind contributions from state level resources, and that's important. But we identify that there's a need for more regional support so that we can think about how to respond to these disasters and provide resources, particularly funding, in a way that is cross-sectoral and both across jurisdictions. And so one thing that we note is that we find that there's a lot of time and a lot of effort establishing conducting vulnerability assessments. But what we don't do is spend the same amount of time with the communities on the ground who are needing to do the disaster response, who are needing to plan for their next intervention. And so there's very little, we didn't see much evidence of long-term or regional thinking. And importantly, a lot of the funding, the implementation of these plans is done in silos. So you can think about them in silos in terms of like how their disaster response might be. And there's very little evidence for a coordinated vision. And this is particularly problemsome if we have disaster events occurring in communities that are lower resourced, that have limitations to health access, and might be experiencing an equal distribution of these hazards. So what we say at the end of this paper, which I'm happy to share, we have a preprint that's available online, and I'll put it on the slides that are shared with the attendees, is that only a minority of our counties that we found managed to connect the different cascading effects in their plans and then translate this into an awareness that corresponds to action on the ground. These are often because we believe that it's because our planning efforts can be restricted by some of these boundaries related to both political and geographic boundaries, that there's a lack of cross-sectoral coordination so that we can reduce our exposure, our critical infrastructure, improve our air quality, and tackle even some of those underlying health vulnerabilities to both smoke and air and poor air quality. We note that there is a need for long-term integrated planning around these cascading risks so that we can operationalize much better the local and regional responses. So with that, I think we can take questions if there is time.
Yeah, then thank you very much for the great presentations from Dr. Catherine Conlon and Caitlin Jones. And here we have 3 questions, but like the time is limited, so I'm going to select one of them and let the 2 of them be answered after the meeting. So from Megan, she says that this looked like such great projects. So have you considered incorporating the new tool from the EPA EJ screen to identify at-risk communities, or it is redundant with the CDPH data?
I can talk a little bit about that. So we have looked at sort of these other social vulnerability indices in constructing the exposure risk profiles, but these do tend to focus more on the sensitivity to exposures themselves rather than the risks of exposures. And so we're really trying to sort of get at that other piece of the vulnerability framework. And so I guess to say, in constructing this, we've looked at vulnerability indices like Healthy Places Index or CalEnviroscreen, which is another environmental justice screening tool prior to the EPA's tool. And we looked specifically at the data that they were utilizing to construct those indicators of risk, and kind of going straight to the source on those data from census and CDPH to try to get specific to what we need for our populations and how we can modify that to look at risks of exposures rather than just sensitivity to exposure.
Okay, so another question is, have you looked at the differences of health impact by jobs? For example, the first responders and firefighters may be most affected by the wildfire air pollutions, but other jobs may also have higher risk factors.
Yeah, thank you for the question. That's a really good point, because it's sort of a limitation to the data that we have available from the census. We're looking right now at occupational industry, which is available from census data, and it doesn't really have a category to look specifically at first responders, specifically firefighters, but we can look at these categories of outdoor workers like construction and agriculture. And so right now we're just focused on, I guess, looking at those areas, outdoor workers, as there may incur increased risk of exposure to wildfire smoke on their day-to-day job. But it is a good point that there are other populations that we will be missing from this.
Okay, great. So so the time is already up. So thank you very much for the presentations, and thanks again for Dr. Catherine Collins and Caitlin Jones participants. So we're going to move on to the next presenters. Our last presenter in the morning is Dr. Alison Aiken and Katie Benedict. Alison's research at LANL, which is Los Alamos National Lab, focus on harnessing state-of-the-art aerosol and trace gas signatures using high time resolutions measurements to reduce uncertainty of aerosols and cloud processes in Earth's energy system. Collaborative in interdisciplinary science to solve emerging national and global security challenges. With over 15 years of experience in experimental aerosols and atmospheric chemistry, we are thrilled to have Alison join us. Also, Katie Benedict is a PhD working in the Earth System Observations Group with Alison Aiken at Los Alamos National Laboratory. So let's welcome them, and their presentation topic is emission factors from laboratory burns of urban fields. Thank you.
So I'll unmute and start again. Sorry about that. So Alison and I have been working to characterize emissions that we might see at the wildland-urban interface rather than just the forest. We know that building materials and homes are increasingly at risk of wildfires for a variety of reasons. When we think about the wildland-urban interface, we know that there, as I just mentioned, that there are these increasing fires. Particularly, we know in California and also recently in Colorado that their fires are increasing in wildlands, but also, you know, neighborhoods are being burned down, partly due to some drought conditions and also some land use changes. And maybe we need to make sure we're managing those interfaces better. But really what we're trying to do with this work is to better understand the airborne toxicity at the WUI. This includes characterizing the gas and the particle emissions from man-made fuels, as well as wildland fuels, traditional fuels, which I will not be presenting about today. If we move here to the next slide, some of the urban fuel building materials that we're looking at are shown here. We have things like oriented strand board, and so you can see that this is a bunch of fibers of wood that have been glued together with some sort of material and might have several different types of chemical additives. These types of woods come in different flavors. So there's this example that has phenol formaldehyde as a known additive. We also might have some other oriented strand board that is not specific about what was added to it. So we're burning both types of those in this work. We can also have more like medium density fiberboard. We probably all are sort of familiar with this type of material. You've seen it somewhere. There are things like pine sheathing. And so that's not quite as glued, it seems like, as something like the oriented strand board, but does still have laminated layers that are being held together by some chemical. We're also burning this melamine particle board. So it's similar to like a medium density fiberboard, but a little bit different. The particles are bigger and it also has this melamine coating. And so we're going to investigate how the emissions from these different types of wood, as well as untreated lumber and pressure treated lumber, which are some of the maybe more commonly and widely used types of wood, differ. And we are doing these experiments in a tube furnace, mainly at 2 different temperatures, but we also do some temperature profiles. And so to give you an idea of what that looks like, we have this tube furnace that we have in our hood. So there's a quartz tube inside this oven, essentially. It's a cylinder. We slide a sample in. We have some airflow over it that carries it to our cyclone. So we get a size cut less than 1 micron. We also have a tank where we hold some of that air so we can slowly sample off for a longer period of time and make sure that our instruments don't get overwhelmed by the really high particle concentrations that we see. So then we also dilute to also help with that. And we're measuring things in the gas phase, like CO and CO2 and methane. We're also measuring formaldehyde and NOx. We're measuring the size distribution of the aerosols, and that includes smaller sizes in the micron, sub-micron range, and also up to 30 microns with a aerosol aerodynamic particle sizer. To also characterize the particles, we are looking at optical properties. So we're interested in these for some of the radiative effects, and we can also tell how much soot or brown carbon is in the aerosol using these measurements. And then more specifically, we can measure the black carbon mass and also aerosol chemistry using an SPAMS. So when we set the temperature of our tube furnace, we can sort of do flaming conditions at really hot or more smoldering conditions at a little bit cooler temperatures. And let's see, this is what some of those experiments sort of look like. Here are 2 pictures, on the left of our original samples. We're taking small plugs. These tend to be less than 0.2 grams. And then if we burn them at 600 degrees C, we see essentially a silhouette that has almost no measurable mass of the original material. But if we burn them at 1000 degrees C, essentially everything is gone. So today, in the next few slides, I'm going to talk about a little bit how we characterize the burn conditions, as well as the optical properties of the aerosol emissions, as well as the emissions ratios. So that's the concentration relative to CO, and then the emission factors. So the amount of material emitted per the amount of mass burned. And when we started using the tube furnace last year, after we finally received it, we realized we had a little bit of a learning curve to do. We were like, yeah, we can just set the temperature and we can control the emissions. But we also didn't account for the fact that, we have a pretty small confined chamber, and sometimes we consume all of the oxygen pretty quickly. And so that's sort of what this plot is showing here a little bit, where we have the temperature on the x-axis and the modified combustion efficiency on the y-axis. And so this is very commonly used to characterize the burn conditions. It's essentially the excess CO plus CO2 over the excess CO2. So close to 1 is flaming. And so we expected, at the higher temperatures, we would mainly have flaming emissions. But then we were having some experiments where The oxygen's dropping below 10% in the atmosphere. We all need it to be around 20%. And so we're getting lower MCEs and even at those higher conditions. So it's sort of exciting because we can have pretty good control. But for these experiments, we know that in a wildfire setting, most of the time we're going to have pretty strongly flaming, non-oxygen limited conditions. And so that's even important, like, we know if is the fire going out, it's still going to have enough oxygen. So we don't want to have too little oxygen even at the lower temperatures. So I'm here just showing sort of the MCE versus temperature space. And for this presentation, I'm not going to be presenting any results that had oxygen limited combustion. That's a different type. And before we talk too much about the results, I wanted to give us a little bit of some definitions for aerosols, just so we can all be on the same page. So when I talk about black carbon, that essentially means we're talking about soot, and that tends to absorb all of the radiation. We don't get any coming back as light. If we just have a purely scattering aerosol, most of the light going in comes back out. There's also aerosol that's sort of in between this, and that's called brown carbon. So it absorbs some of the radiation, but it also scatters some of the radiation. And we use two different metrics to sort of describe this aerosol. We have the SSA, which is the single scattering albedo. And this is essentially this ratio of the scattering, the light that's scattered, to total extinction, which that would be the sum of the absorbing and the scattering. So if we have an SSA of 1, means it's a purely scattering aerosol. 0.2 would be, it's like 80% absorbing. And then we have the absorption angstrom exponent, or the AAE. And this indicates the spectral dependence of the light absorption. So it might give us an indication of the brown carbon versus black carbon, for instance. So we're going to start, though, with the physical properties of the aerosols we observed. So when we think about a size distribution, we're looking at the volume mean diameter. So where most of the aerosol fall with respect to their volume, which is better than number, because we can have a lot of small particles, but they don't take up very much mass. So the volume mean is a nice way to look at that. And here I'm plotting the volume mean diameter versus the temperature. And then I have our different fuels and these different symbols here. Our oriented strand boards are the triangles. Our more particle board, medium density fiber boards are the circles. Pressure treated are these plus signs. And then we have our dimensional lumber. And so we don't really see like a very nice clear trend. We see there's a lot of scatter at 600, where we did a lot of our experiments. And it's a little bit narrower at 1000 degree, where we also did most of our experiments, but there isn't necessarily a consistent trend. And if we go here to the next slide, I'm showing it in a little bit different space. And instead of showing the averages that we saw, I'm showing the points for all of the burns. And instead of temperature, I'm showing the MCE this time. And so we can sort of see here that there's a triangle type shape where we see a lot of variability at the more flaming conditions. Those sort of, combine together, merge together at the lower MCEs. It seems like there isn't, a very good trend, but we do just see a lot of variability. But I would say I don't think that the volume mean diameter is the most important metric when we're talking about the emission factors, but it's a nice way to think about the aerosol and whether maybe it's fractal and sooty or if it's compacted. If we compare the fuels in a little bit, this is a little bit nicer way to look at how they vary by fuel type at the different temperatures. We see on average, the higher temperatures in the yellow bars, those burns have larger aerosols. And that could be because of they're more fractal and larger soot type particles than at 600 degrees, but we see still quite a bit of variability. And that could be related to inhomogeneities in the fuels themselves, especially those ones that are glued together. We're not having a consistent type of sample every time. There's not the same amount of glue and the same amount of wood. If we move to thinking about the black carbon content, this is sort of reinforcing what I was saying about the 1000 degree temperature burns. At the higher temperatures, the black carbon fraction is 1. So that means essentially all of the the aerosol is black carbon. And so it could just be that we're not really doing a good job sizing it because so much of it is black carbon. We tend to see repeatedly at 600 degrees that it really depends on the sample, the type of burn conditions that we observed. But we see this sort of really nice transition, especially if you focus sort of maybe on the gray pine plywood sheathing points that follows here, where we see that the aerosol changes from this black carbon to other types of organics. And this type of result tends to be very similar to natural fuels, which I'm not showing directly here. And then I mentioned the absorption angstrom exponent. So this is, the wavelength dependence of the absorption. And, we just saw that at 1000 degrees, we saw mostly black carbon, and a AAE of 1 indicates it's almost purely black carbon. When we go higher than that, it indicates we have more brown carbon, and that's what we consistently see here. But we see that this wavelength absorption dependence really varies from fuel types. So for instance, our pressure treated fuels have a much higher AAE and consistently higher than something like the particle board, which was very similar actually to the 1000 degree burns for the both temperatures. I also changed this. This is a common space where we look at AAE. We look at AAE versus SSA, and we see that the burns sort of break out into the high temperature flaming, as I just mentioned, close to 1, all down here at low SSAs because it has a lot of black carbon. And then at the lower temperatures, we see more black carbon formation, and it really varies. I think the oriented attic pine, oriented strand board, the slightly darker blue triangles are really like they have a nice linear relationship right here. Whether that's robust over more time, I don't know. But it's a nice way to think about it. If we put a fire out, but it's not completely cool, maybe there are still hot spots, you might have more of these type of emissions than when it's fully raging and really flaming and hot, where you're going to have almost purely black carbon. So if we spend a little bit more time thinking about the single scattering albedo, here we're plotting it versus temperature. And so this has the exact opposite S-curve as the black carbon, as we would expect, right? At the lower temperatures, we know there's very little black carbon, and so we have almost purely scattering aerosol. But as we move up into the higher temperatures, it's mostly absorbing, but there still is a scattering component. But it's pretty consistent across all fuel types. We do see a little bit of separation here between the MDF and the particle board, which aren't quite as absorbing as the other fuels. And if we directly compare the 600 and 1000 degree burns again, we see that for some fuels, there are pretty large differences, as we saw before. But in other cases, like for this oriented strand board, there's no statistical difference because we saw so much variability at 600. And that's partly a reflection of, the burn conditions at 600. Looking back, we probably should have chosen a slightly different temperature where the transition in burn conditions didn't occur, that we were definitely in more of a smoldering range. If we move to emission ratios, so this is the excess formaldehyde observed over the excess CO. We're starting here with formaldehyde, and I'm comparing the burns at the two different temperatures. And so we saw almost no formaldehyde emitted at the high temperature burns. The exception to that is the medium density fiberboard and the particle board, as well as the OSB, which we would expect maybe those have more of those glues that might contain formaldehyde added than some of the other materials. But at the lower temperature, we have a lot of variability depending on the fuel type. You can see I cut the scale here so we could see all of the detail at low values, but for instance, the attic pine oriented strand board, we had an emission ratio up to 8,000. But in general, you know, it's hard to say exactly what's happening with those. I expected, like, for instance, the pressure treated boards to be more similar because this one, the ground contact one, is treated slightly differently, but I don't think significantly. So I think spending a little bit more time trying to figure out exactly what's going on here. But in comparison to wildland fuels, this is sort of a similar range. In terms of, they see things up to about 50, but also, you know, those observations tend to be from further away, and so could be a combination of primary emissions and secondary formation. While for our laboratory measurements, we measured them really close to the source, and I also looked at the time traces to make sure that we saw an initial increase in the concentration. And it wasn't a delay that might indicate more of a secondary formation, which is also important, but not what we were trying to characterize. If we move to thinking about NOx, these are plotted on separate charts because the 1,000 degree burns had much higher emission ratios than at 600 degrees. Again, I don't think we saw a consistent pattern across, you know, we don't see the same trends for the fuels at these two different temperatures. And there might be things going on that we haven't really thought about in terms of, you know, the composition and how they're being broken down under these different burn conditions. If we move to emission factors, so this is actually a really nice way and what's more commonly used when we think about putting them in models. So this would be the grams of material emitted, in this case CO2, versus the kilograms burned. And here I'm just showing CO2, which maybe isn't the most exciting thing when we're thinking about toxicity, but these break apart really nicely. We can see how the different materials, like the pine plywood sheathing, separates from some of these other fuels that are more consistent, you know, with like the OSB in the blue triangles. I've also added the emission factors from the earth block samples that Michele gave to us, which I have a feeling we might be hearing about this material later. So, but this is, his group is working on is a different type of sort of fire resistant building material. And so we offered to characterize the emissions from it. And so you see that the emission factor of that is much lower than any of the other fuels. Next, we look at NOx. And so NOx is a little bit variable. You know, we don't really have the same trends. You know, for the OSB, then light blue, we see maybe a slight increase. One of the interesting things is that these earth block samples are on the medium to high side and sort of have the opposite temperature trend, but that where there are higher emissions at the lower, or emission factors at the lower temperatures, but those are consistent with the fiberboard and particle board in these circles as well. And then if we move to the formaldehyde emission factor, these tend to be pretty low at high temperature relative to the amount of mass burned. So on the left is at full scale, and then the right, I just zoomed into 600. I thought I drew a box, so I apologize for missing that. So we see, you know, they don't show up on this left plot at the higher temperature. We see quite a bit of variability at the 600 degrees C temperature, and OSB is really high over here as well, but it sort of seems like an outlier compared to this low one at 400. But it's a little bit unclear why that's happening right now. So if we zoom in to all of these ones that appear to fall at zero, you know, some of them do fall at zero, but some of them we see, you know, emission factors on the order of, you know, 50 or 100 grams per kilogram. You know, the pressure treated lumber also we see pops out here at 600. I do think that there's some thermal decomposition that could be happening above 700 degrees for the formaldehyde. And so that could be one of the factors in the low emission factors there as well. And if we think about the total amount of aerosol emitted, and this would be just the total amount below about 500 nanometers. I haven't included the larger size range in this data set yet. We see more aerosol is emitted at the lower temperatures, which is shown here. Again, this is zoomed out. And then on the right, we have the scale just going up to 2. And so, you know, we see like the earth block samples are low, almost 0 in both plots. So that's like pretty positive for any type of building material where you're not going to have maybe as many PM emissions. You know, for the 600 degrees C, we do see that there are, you know, a lot more emissions at the lower temperatures, sort of as this ramps up. And we saw quite a bit of variability at 1000 degrees C, but no consistent trends is what I would say in terms of how the different types of wind materials have sort of fallen out here. You know, maybe higher for the MDF again. But still, we saw a lot of variability, and some of that can be attributed to the burn conditions, which we were trying to control, but we, you know, couldn't have the same MCE every time. And so maybe I need to sort of rethink about how we're showing this so we can account for some of that as well. So just to summarize here, we looked at 8 different building materials. We saw that black carbon was emitted, you know, predominantly at the higher temperatures above about 650 degrees, definitely at 1000 degrees and above, it would be mainly black carbon or sooty stuff. You know, the formaldehyde emissions were variable, but some of the materials did emit more formaldehyde than what we tend to see in some of the wildland fuels, but not significantly different. Maybe we would thought that they should be more different. We still have work to do to analyze the AMS data for the mass spectral chemical data to look more a little bit at what the actual chemistry of the particles coming off these different fuel types are and what that means for various impacts. And I will stop there.
Okay, thank you very much for Katie's presentation. So let's move on to the Q&A sessions. So our first question is from slide 13, how the black carbon fraction is calculated.
I'm like, can't find myself here. We take the total aerosol measured by the SMPS, which measures between 12 nanometers and 500 nanometers. And we assume a density to calculate the total aerosol, and we use the SP2 for black carbon mass, or if that wasn't working, we have a PAX that measures aerosol absorption at 870 nanometers. And we convert that to a black carbon mass using a MAC value.
Okay, so our next question is, do we feel a need for more laboratory simulation experiments with low temperatures smoldering?
You know, I think that's a little bit of an open question. You know, when I've talked to Michele before, you know, he has been most interested in the highest temperature burns we could do. So 1000 degrees and 1100. I do think there are some interesting things that happen at lower temperatures, but when we think about the wildfires that have been happening, most of them happen at these really hot, high temperatures. So, you know, for this project, we're focusing on the higher ones. We tried to do some of the space so we could understand some of those changes. I do think in the future, we will focus on more of the lower temperature burns. And I didn't mention, but we're also going to focus on some of the other materials you might find in your home, like carpet samples and flooring samples and fabric samples.
Okay, thank you very much. And thanks again for your fantastic presentations. So right now we've finished all the presentations in the morning. So I'm going to handing the moderator back to Professor Macali-Barbatos. So Professor, we finished the morning sessions.
Yes, again, I wanted to thank everybody, the presenters, the panelists, and the attendees for being with us. I hope you found the presentations interesting, and I invite you to take a lunch break. It's a little bit more than 1 hour. We'll resume our program at 1:20, and we will have 2 more sessions on wildfire emission prediction, air quality assessment, and on development and assessment of wildfire mitigation strategies. So look forward to seeing you all back after lunch. Thank you. Hello, everybody. Welcome back to the afternoon part of our symposium. We have still several presentations before the end of the day. And I thank you very much for attending the first part of the symposium. And I believe the second part will be as interesting as the first part. And so without further ado, I'll let Nitin, freshly minted doctor of the Department of Civil Environmental Engineering, who will be moderating this afternoon presentation. Nitin, please go ahead.
Thank you, Dr. Barbato. So we have Dr. William Lossman for next presentation. Dr. William Lossman is an atmospheric scientist with experience in air pollution, atmospheric chemistry, and the boundary layer. He did his master's and PhD at Colorado State University, working on wildfire smoke impact on human health and on emission and dispersion from human feeding operation. He is currently a postdoc at Lawrence Livermore National Laboratory, where he works on numerical modeling of wildfire emission and smoke dispersion. With this, I welcome Dr. William Lossman for next presentation.
Hi, can everyone hear me?
Yes, we can hear.
Perfect. Okay, I'm going to share my screen then. And we're all seeing my slides now?
Yes.
We're good to go.
Great. Well, I'll get started then. Thank you for the kind introduction. As Nitin said, my name is William. I'm a postdoc at Lawrence Livermore National Lab, and I'm going to present some work that we've done, which is a case study of the 2020 Northern California wildfire season and the effects on air quality. I'd like to take a moment to acknowledge all of my co-authors who are listed on the slide, and with that, we'll begin. And it would be remiss of me to not begin with a little trip down memory lane. Many of us, I think, on this call are either in the Bay Area or somewhere in California, or we have some other connection with wildfire, which is why we're interested in this topic. I remember very clearly at 3:30 in the morning of August 16th, 2020, waking up as a lightning storm rolled through the Bay Area, which is not a very common thing to happen. There were numerous lightning strikes all over the hills surrounding the Bay Area. And then after the storms, temperatures increased, winds picked up, and we got a number of wildfire complexes that merged into large fires all over the area. And so I'm showing a map of San Jose, San Francisco, Livermore, where I work, Fremont, where I was living at the time, and 2 perimeters of fires that grew during this time period. And this one, especially the SCU lightning complex fire, was associated with numerous evacuations throughout the area. And though I was fortunate to not evacuate my home, I did experience smoke from these fires on a daily basis for the better part of a few months. And so this is a picture of smoke from a prescribed fire that was set as part of a fire break to try to contain the SCU lightning complex fire. Meanwhile, on the other side of the state, the Creek Fire started east of Fresno in the Sierra Nevada mountains. And this fire is notable because it produced a pyrocumulonimbus cloud that reached 55,000 feet above sea level, which is the highest ever observed smoke plume. And it produced 2 fire tornadoes, an EF2 and an EF3, that caused many dramatic evacuations of hikers and outdoor recreators. And fortunately, no lives were lost in this blaze, but this is another notable event during the 2020 fire season. Finally, during the period from September 8th to 15th, a series of fires from Oregon produced smoke that went out over the Pacific Ocean and then was entrained in a synoptic scale weather feature, which then inundated most of the Western California with smoke, as you can see in this satellite image from MODIS. And this event was notable because of the many pictures, such as the ones I'm showing here, depicting an orange sky over San Francisco. And this was caused by a dense layer of smoke sitting on top of a marine layer of air near the surface. And this was all over national news and social media. And the interesting thing about this specific event was that for the first half of it, up until about September 11th, surface air quality was actually not bad because of the cold, dense air sitting close to the surface. It kept the smoke up high. However, as time went on, the smoke gradually mixed down and air quality became quite poor near the surface. And for those of you that are reminiscing with me about these series of events, or thinking, wow, that was a lot, that was all 1 month of one fire season. But it was the worst fire season in California so far. So what I'm showing here is area burn on the y-axis and year on the x-axis. And so we can see from 2010 up until 2021, there's this steady increase in fire area in California, with 2020 being by far the worst season. And this fits into the bigger picture of long-term trends that are well understood at this point, that high spring and summer temperature is associated with more frequent and more intense wildfires. And that's what this figure from Leroy Westerling's paper shows, that as spring and summer temperatures have increased historically, there's been an increase in the number and frequency and severity of wildfires. And this is going to continue as climate continues to warm. Now, one of the things that I care about when it comes to wildfires is smoke, because smoke has the potential to impact large fractions of the population. And so what I'm showing here on the left is a map of PM2.5, or aerosol particles smaller than 2.5 microns in diameter. And these are associated with a number of respiratory and cardiovascular health outcomes that are negative. And so exposure to more of these particles is bad for public health. And so these 2 studies by Colleen Reed derived a statistical model for quantifying PM2.5 concentrations in response to wildfires. And so we can see a time series of these PM2.5 concentrations in this panel on the right. And anything above 35 micrograms per cubic meter for 24 hours is considered hazardous, according to the EPA. And anything more than 100 micrograms per cubic meter is hazardous on short time scales. And so during this fire season, Reed et al. Were able to derive a number of relationships between health outcomes and smoke exposure. And so this left panel are respiratory hospitalizations, and then we have respiratory emergency department admissions. And the x-axis of each of these panels is increasing concentrations of surface PM2.5. The y-axis is what's called a response ratio. So you can think of a value of 1 as being no deviation from baseline asthma or respiratory hospitalizations. So an increase of 0.6 for asthma means that there were 60% more asthma hospitalizations than normal during a fire event. And so these different concentration response functions look different for different diseases. However, in order to derive these concentration response functions, we need highly accurate estimates of how much smoke people were exposed to at the population level. And so this is a lot of different plots showing many different health outcomes for different male and female sections of the population. And this is from a different study that was done in Washington. And one of the things that's interesting, if we look at this COPD panel, is that depending on the method you use to quantify exposure, you get a totally different answer. And this is a phenomenon called exposure misclassification. Essentially, we're misclassifying how much smoke parts of the population are exposed to, and this is causing us to attribute their health effects to the wrong cause and can really confound our efforts to do accurate health impact assessments of wildfire smoke. So current methods to simulate population exposure to wildfire smoke are insufficiently accurate in order to reduce exposure misclassification in health studies or to plan minimally invasive interventions to protect the population from smoke. And so there is a need to understand how accurate our current methods are and to improve accuracy. So I'm going to be talking about one of the many tools that exists to quantify human exposure to wildfire smoke, and that's chemical transport modeling. Specifically, this uses a model to simulate the weather and atmospheric processes. It ingests information about the atmosphere's current states and boundary conditions of your simulation domain to calculate things like wind speed and direction, atmospheric stability, and can include complex marine and topographic effects. And so this is responsible for producing weather that's conducive for wildfires, but also advecting emissions from wildfires around. We have another submodel that simulates the fire physics. And so this can be used to quantify the heat and moisture fluxes from the fire, which are produced by the combustion, but also the location and intensity of the combustion as it occurs and the kind of fuel being consumed. And finally, we have a model to simulate the chemistry and aerosol processes that occur within the smoke plume in order to produce the harmful PM2.5 that ultimately has large effects on human health. And the modeling framework we're using actually includes components for all of these things, and they talk to each other. So the heat from the fire can affect the winds, and the winds can affect the fire. Also, perhaps less intuitively, smoke can affect the solar irradiance on the surface, which can have impact on the temperature and wind speed, which can also impact the fire spread. And so this model is able to calculate the interdependencies of all these different subcomponents. And this model is called WRF S-Fire Chem, the Weather Research and Forecasting Model with S-Fire and Chem. And so before I go into more detail about the S-Fire component of this model, it's useful to understand just WRF Chem and how do we do these kinds of studies historically. So typically, when one wants to do a WRF Chem simulation of wildfire smoke, one would use something called a biomass burning emissions inventory, which is essentially spatial and temporal information about fires and the emissions that they produce. The emissions inventory that we are going to look at in this study is FIN, the fire inventory from NCAR, which uses MODIS fire detections and land use classification to estimate emissions fluxes. There are a lot of pros to using this kind of approach. FIN, for example, is available at 1 kilometer spatial resolution, daily temporal resolution in almost real time, which means that, and FIN is available all over the world. So if you want to simulate a fire that's happening in the Congo rainforest 2 days ago, you can with FIN. We also know the satellite products that are used in producing FIN and understand their accuracy and precision. And these kinds of approaches are well tested and validated. They're not perfect. They do suffer from some weaknesses, which I will discuss, but we understand those weaknesses and the kinds of accuracy that we can get with this approach. The cons of using something like a biomass burning emissions inventory is that you can't know anything about the behavior of a fire during a given day. If a fire grows from 1 p.m. till 7 p.m., that is not represented in these kinds of data sets. 1 kilometer resolution may be insufficient for some applications as well, if you're interested in fires that are burning in complex terrain or close to the wildland-urban interface, for example. There are also issues representing the plume rise and the atmosphere without the fire. So none of these processes are included directly in the larger atmospheric model, and so they must be parameterized, and those parameterizations can have problems. So in summary, FIN and emissions inventories in general are best suited for larger scale problems. We're describing fire behavior with climatology sufficient and data, and the specific strength of FIN is that data is available so rapidly that it is a very useful tool for these kinds of simulations. However, FIN will face challenges when detailed fire behavior that deviates from climatology is necessary to properly quantify air quality impacts. In contrast, a tool like S-Fire is useful because it allows you to solve for the fire front in real time. So S-Fire uses specifically the Rothermel semi-empirical fire spread model and the level set method to calculate the advancing fire front. And then it uses something called the burn-up model to represent fuel consumption behind the flame front. The pros of using a fire spread model like S-Fire is that you can calculate the fire location and intensity at arbitrary spatial and temporal resolution. So you do not need to make any assumptions about how the fire behaves during the day. Fire locations can be highly accurate and precise if your simulation is good. And of course, S-Fire is a model, and so it's never perfect. And then finally, S-Fire, because it computes heat and moisture fluxes, you can have a physics-based plume rise without inferring any of the inputs to and relying on a parameterization that you would need in the absence of a model like S-Fire. However, this comes with some cons. S-Fire can require a lot of parameter tweaking, especially initializing your fire properly in order to get a realistic or accurate solution. And this causes S-Fire to be intractable for larger scale problems where there's many different fires burning at the same time that all need to be optimized separately. Furthermore, S-Fire model development has historically been prioritized around accurate prediction of fire spread. And so the physics of the fuel consumption behind the flame front relies on some generic data and does not include processes such as smoldering combustion or the ability to represent larger fuel elements. So S-Fire is best suited for smaller scale problems where it is feasible to tweak parameters and perform ensemble simulations to find optimal model solutions. S-Fire will face challenges for large domains and longer timescales where many different fires occur with different kinds of behavior. However, this has changed recently. And so I'm showing the abstract or the reference of a paper that came out that uses a machine learning model to ingest active fire satellite data and produce fire arrival times. And so this allows us to initialize and run WRF S-Fire with solutions that we know are accurate for many different fires without a lot of the parameter tweaking and optimization that used to be required. And so this actually allows us to scale S-Fire up to larger domains. And so that's what we're going to try to do in this study. In this study, we conducted 3 different WRF chem simulations: a control simulation with no representation of biomass burning, a reference simulation that uses FIN, the biomass burning emissions inventory, and a third simulation that uses a fully coupled WRF S-Fire chemistry model with online fire and chemistry. And we simulated a month-long period. The fire started a few days after August 4th, but this allows us to spin our model up properly. And we nest down to an innermost domain of 1 kilometer resolution. And the scale of this problem is actually right in between where we expect a model like Fin and a model like S-Fire to do well. So this is actually an intermediate scale where we expect both models to struggle. And so it'll be interesting to compare the performance. And so the first thing we look at is the fire area, which determines how big are fires and what kinds of fuel are being consumed to produce the emissions. So I'm showing on the left the emission area from S-Fire. Red areas are active fire and blue areas are areas where all the fuel has been consumed already. So in S-Fire, these blue areas can no longer catch on fire and can no longer emit smoke. Fin is not constrained the same way. Fin will allow there to be a fire wherever there's a fire detection in the satellite. And so we can see that the fire detections are kind of blotchier. There's less continuity in the fire. And finally, we compare this to GOES, which is a geostationary satellite, which has a separate fire detection product. And we see qualitatively that these fires seem to agree on where the fires are for the most part. If we look later in our time period, we start to notice some differences. And these differences are largely due to the fact that S-Fire has consumed a lot of the fuel that Fin seems to think is still on fire. It's also noticeable to look at the creek fire. According to S-Fire, most of the fire has already burned by September 7th, whereas Fin and GOES both suggest that a lot of the fire area is still active. And so this is one of the shortcomings of using something like the burnup model to represent fuel consumption behind the flame front in S-Fire. So if we integrate the total fire area in our domain, a few things jump out at us. First of all, S-Fire, which is in the blue curve, has much more fire area than Fin does. Especially early in the time period, there was rapid growth and there's almost a factor of 4 more fire area. This, of course, changes to be more like a factor of 2 for the rest of the simulation. There's also some differences in the timing of the fire growth at the end of our time period. Fin seems to think that the fire grew on September 7th and 8th, whereas S-Fire had the fire growth a little bit earlier. I've overlaid the GOES-R domain integrated fire area on this plot, and we can see that it seems to agree with S-Fire at the beginning of the simulation, and maybe it agrees with Fin in terms of the absolute fire area through the rest of the simulation. Though it is important to note that the GOES-R fire area product is new, and so it's unclear to me that, for example, this increase in fire area that the satellite product is showing is real. It could be an artifact. So what does this mean for PM2.5? I'm showing surface PM2.5 concentrations. The top panel is on August 20th. The bottom panel is on September 7th. Left is S-Fire, right is Fin. And if you look carefully, I've overlaid surface measurements in these points, and they are on the same color scale. So darker points mean more concentrated PM2.5. And so what jumps out to my eye when looking at these figures is that S-Fire is estimating much, much higher concentrations of surface PM2.5. And this can be attributed to the larger fire area. In these measurement sites in the Central Valley, S-Fire seems to even be under-predicting the PM2.5 concentrations, but it is suggesting that the concentrations are elevated in this region. Fin, on the other hand, does not put any smoke in that area. So on this particular day, S-Fire looks like the more realistic solution. However, the narrative is a little bit reversed on September 7th, where these same sites in the valley are showing little or no elevated PM2.5. And that seems to agree better with what Fin is suggesting is happening than what S-Fire is suggesting. So if we look at a single site, I've chosen Livermore, but that's a somewhat arbitrary choice. We can compare directly the Fin PM2.5 in blue to S-Fire in orange, and then the measurements in these circle points. And I've overlaid 35 and 50 micrograms per cubic meter as sort of references for somewhat unhealthy and severely unhealthy concentrations of PM2.5. And a few things jump out to my eye. First of all, S-Fire massively overpredicts surface PM2.5 concentrations at the beginning of the time period. And if you recall, this is when S-Fire had a factor of 4 more area burn than Fin. What happened here is we think S-Fire overpredicted the rate of spread in a lot of fires. And this is actually expected behavior from the machine learning model that was used to derive the fire arrival times. We also noticed that neither simulation gets the elevated PM2.5 at the end of the time period. And this is what I was talking about earlier, where there was long-range transport from Portland and a complex marine boundary layer that kept the smoke, the PM2.5, far from the surface at first, and then degraded surface air quality later. And there was something in those dynamics that our models missed. Both models had represented emissions from those Portland fires, but those were in domain 2. And so the long-range transport is difficult to get right with these kinds of models. And this is somewhat consistent with all the other, with some of the other measurement sites that I've selected here. And I've picked Livermore, a few other Bay Area sites, and then Modesto and Sacramento to get an idea of what's happening in the valley. But apart from these, the beginning and end of the time period, it's not straightforward to pick a winner from these simulations. S-Fire certainly predicts more PM2.5, but both simulations seem to capture the general trend about what times concentrations were elevated, but they don't really reproduce the exact temporal behavior. And so any kind of correlation analysis will not be very flattering for either of these simulations. In order to try to quantify performance, we did a binary analysis. So what I'm showing here is daily average simulated PM2.5 on the y-axis and observed PM2.5 on the x-axis. So if the model was perfect, every point would lie on this one-to-one line. And then I've chosen a threshold of 35 micrograms per cubic meter to indicate unhealthy or healthy. And we did a binary analysis. So we looked at true positives in blue, true negatives in purple, false positives in orange, and false negatives in red. And the takeaway from this plot is that S-Fire has a much higher negative predictive value than positive predictive value, meaning that 55% of the time PM2.5 55% of the time PM2.5 concentrations were not impacted by smoke, S-Fire got it right. The positive predictive value is not as good, and that's just due to the high number of false positives. If we compare this to Fin, we notice that there's just lower concentrations in general. So that this leads us to have a higher true negative result, but also a higher number of false negatives. And it winds up being a wash. We have similar statistical performance. So the two figures I just showed are this panel, the top left and bottom left respectively. I included similar figures for the daily max PM2.5, and I selected 100 micrograms per cubic meter as the threshold there, as that's the cutoff for an unhealthy or hazardous AQI. And we wind up with a similar story. S-Fire does a better job of predicting the true positives, but it is really better and it really has better negative predictive value. Fin, because the concentrations are lower, this results in a smaller number of false positives and a larger number of false negatives, and the statistical performance is similar. So in summary, we looked at the 2020 California wildfire season, which was the most intense on the record. We conducted air quality simulations using these two approaches. We didn't find a big statistical difference between the two approaches. However, it is important to know that with WRF S-Fire, there are some low-hanging fruit in terms of model upgrades that we could use to improve these simulations in the future, such as using more accurate data about fuel combustion rate and fuel loading and initially and finally after the fire in order to better constrain the net emissions flux. This would also allow us to better estimate the heat flux and moisture flux and give us more accurate estimates of plume rise. And so that should be a powerful model improvement that is currently something that we're thinking strongly about. Finally, I wanted to tease one more result, and that is that wildfire smoke has these impacts on temperature. And so what we're looking at here are temperature on the left and wind speed on the right. And this is the difference between our WRF S-Fire Chem simulation and our WRF Chem simulation with no representation of fires at all. And this is an average for the entire month. And so there were places where the temperature was 4 degrees cooler for the entire month because of these the smoke plumes. And that's because on individual days, temperature was suppressed as much as 10 degrees. And anyone who's lived through a smoke event knows this. When smoke has been out, temperature is cool. It makes sense. The smoke absorbs or reflects the incoming solar radiation and keeps the surface cool. What is maybe a little bit less obvious to most people is that this can have an effect on the wind speed. So I'm showing that wind speed was suppressed by as much as 2 meters per second throughout the entire domain. And this is because in California, we have a complex interaction between marine and orographic heating, which creates all of these wind flows and microclimates. And with smoke in the area, we shut a lot of these circulations down. And so as fires become more frequent and more intense, we expect more smoke. And this might have implications for human health, but it also might have implications for things such as wind energy and solar energy production. And so this is something that we need to spend more time researching because this is just a model result, but it's an interesting thing to think about. And with that, I'd like to thank you for listening, and I'd like to take any and all questions.
Thank you, Dr. William Lossman. So we have one question here, and the question is, can the misses of the model at the end of the fire event be connected with a smoldering condition? And the second question from the same attendees, are the model considering shouldering fires?
Yeah, so let me answer that. I absolutely think that missing the smoldering in S-Fire is a big reason why we are not getting the fires right at the throughout our simulation domain. However, it is important to point out that there's also this long-range transport. So if you're referring to those bits at the very end of the time period, I think that's more an issue with the long-range transport. I didn't show it, but we looked at a lot of satellite images of smoke and then some AOD, aerosol optical depth plots of our model simulations. And so we weren't getting those Portland fires to put smoke in the right place. And so in order to use measurements to evaluate these simulations, you have to get a lot of things exactly right, or you wind up with totally the wrong answer. And that's kind of along the lines of the second question, which Evan Ship asked, did our model evaluation take into consideration grid averaging or nearest grid estimates when comparing point measurements to model estimates? Good question. Yes, we did. We interpolated from the 4 nearest grid cell centers to each monitoring site. So we did take the grid averaging into consideration. In my experience, we could improve our agreement to the measurements if we did some spatial smoothing of the smoke. We ran these simulations at 1 kilometer resolution, and if we were to aggregate to 4 kilometer resolution, for example, we would get smaller, less steep concentrations and broader smoke. And I think that would go a long way towards improving the agreement with the measurements. But that's just because we can show statistically better agreement by smoothing doesn't mean that there's more value to those smoke simulations. We want to be able to simulate the smoke correctly at high resolution in order to accurately distinguish between health effects, because there are population gradients on 1 kilometer scales.
Okay, so yeah, we still have some time. If someone else have a question, please do ask. So in the meantime, I have one question, like the model you have, will it also work on the WUI region where we have like a urban population like houses? So will it also consider the emission from the structures?
So the emissions that we calculate are based on emission factors, which are only exist in the literature really for biomass at this point. I know there's some work at LANL to find emission factors for urban fuels. And so that's something that we're interested in incorporating in our simulations, but it's not in there yet. So yeah, it was just biomass emissions. Now, spatially, the fires can burn into the WUI if that's what the satellite imagery shows, or that's what S-fire predicts. Though I will say that S-fire rate of spread through WUI is not calibrated for those kinds of fuels.
Okay, so we have one more question. It says, what version of WRF and S-fire were used?
That is a good question. I don't remember off the top of my head. I want to say it's WRF version 4.1, 4.2, and the similar S-fire version. The version that we used was cloned from the Git repository early 2020. So that should hopefully give you enough context.
Okay. So yeah, let's move to then next speaker. So next speaker, I welcome Dr. Quinn Hart, and he's an application developer for UC Davis Department of Land, Air, Water Resources. Currently, he is working on a number of projects, including the CERES project. It is CERES project, and its application site CASIL, CASIL, which are both primarily concerned with making more environmental information available to California public. CASIL is a repository for GIS data, and CERES does everything else. Along those lines, Dr. Quinn works on COMET project, which intend to combine a number of different distributed data sets having to do with environment and climate change for a strip of California from Bodega Bay to Lake Tahoe. Currently, Dr. Quinn has a project with California's CIMIS program, where he combines GOES weather satellite data with surface measurement to provide estimation of evapotranspiration for California. Evapotranspiration is a measurement of how much water plants need for a particular day. The information helps farmer determine how much to irrigate or give water management an idea of water use in their area. Dr. Quinn manages the satellite station for that imagery here at UC Davis. And with this, I welcome Dr. Quinn Hart for his presentation.
Excellent. Thank you. I hope everyone can hear me, and I'll see if I can take my screen. And hope everyone can see that as well. Is that the case?
Yes, it looks good.
Excellent. Thank you so much. So yeah, thanks for that introduction. My name is Quinn Hart. I'm actually no longer at Land, Air, and Water. I'm now at the UC Davis Library. But kind of some of the background that I had in the GOES and the evapotranspiration model is a good introduction to this talk, which is titled Real-Time Updates to the GOES Weather Data Processing. But what it really is for us to begin looking at some of the real-time data processing that we created for that evapotranspiration project, and see if we could apply some of those same lessons to wildfire and air quality mapping. And my colleague, Justin Mers at the library as well, did the most of the architecture of this whole thing. I'd like to acknowledge that. Unfortunately, he's not able to make that presentation for today. But what I'd like to do is really just do a quick introduction about the GOES-R weather satellite. We had a good introduction in the previous presentation as well on some of the products there. And then kind of look at lightning mapping, which is one of the areas where we looked at taking the GOES satellite system that we use and expand it to areas that we're more interested for wildfire mapping. And that kind of, I hope, leads into a reason for wanting to have a more real-time data processing closer to your area of interest, closer to California for us. And for that, I'll describe the architecture that we're developing for that. And then from that architecture, I will go and do one more example application that looks at thermal anomalies during the fire season as another example of using real-time data sets. And then kind of just finish with a few lessons learned and things looking forward. So the GOES-R or the GOES 17 and 18 satellites, they're kind of the same thing. The GOES-R is a series of satellites that's NOAA's most modern weather satellites. Once they put them into space, they get numbers. So GOES 17 is what's currently over GOES West. It's actually a pretty new satellite. It was launched in February, well, it was launched in 2018, but it started to cover the West in February of 2019. But it's always had a little problem with some cooling of some of its detectors. And so as a result, you couldn't get continuous coverage for every one of the products. So they just in the last week or two launched another GOES-R satellite and successfully, and that will be slowly moving across to the west and will replace GOES 17 sometime predicted in August of this year. And then we'll have a fully operational system up at that point. GOES has a number of different sensors on it. Today we'll be talking about the geostationary lightning mapper, and then we'll also be talking a little bit about the advanced baseline imager. So the baseline imager is by far the most important sensor, I would say, on the GOES satellite imagery. Because GOES is a geostationary satellite, you can get very, very high repeat time. I mean, on the order of 40 images an hour over California in 16 spectral bands through the visible, into the near IR, in the mid-range infrared, and into the thermal as well. And with all of these wealth of bands, that's what gives it its ability to develop a number of weather-related products. And the resolution of a GOES satellite image varies from about 500 meters per pixel to about 4 kilometers for some of their other sensor areas. There are some other instruments on GOES as well. Some of them look, for example, at the solar activity, but we won't be talking about those in this presentation. So we have a project here that uses GOES data primarily for terrestrial applications. So the idea is that there's a primary use for GOES for weather satellite imagery, but because you're able to look at the surface so often, there's a lot of other reasons to use it too. So in the introduction, we heard about the evapotranspiration products, where we use the GOES data to predict what the net solar radiation is for every day. And that's one of the key features that goes into the estimates of potential evapotranspiration for California. And that's the production product that we're using now. But you can understand that if you're getting these estimates of net solar radiation on the order of minutes, you can do a lot more with that. So we've been looking at the possibilities of predicting what your solar power potential might be, or combining that with thermal to predict what the demands might be in the upcoming areas, or even combining them again to see what the distributed demands and potential exist on a distributed power grid. You're also able to look at immediate events that are happening very quickly. So, for example, an inundation event that quickly has a quick amount of flooding due to a levee break. is something that you can pick up relatively quickly because of the fast repeat time that you have on GOES satellite imagery. Similar with the thermal bands, you can see where the skin temperature of California is really heating up quickly during the day. And then now with this project, with this collaboration, we're looking at what kind of applications we can have both for wildfires and for air quality mapping. And so what I'm going to talk about first is the geostationary lightning mapper, or the GLM. We were asked to look at the complete record of the GOES 17 lightning strikes since it's been up through 2019. And this was before we have real-time access to that. So just a quick explanation of the GLM data product. You can think of that as a single camera inside the system that is can very accurately find quick strobes of light. And so this is actually using the near-infrared, nearly visible light that comes from lightning strikes in the clouds. And on the left-hand side of this, you can see these pixels. You probably can't see Lake Tahoe in there, but it covers about 4 pixels or so. So the pixels are relatively coarse for the GLM. They're at about 7-kilometer resolution. And when you get a flash, you might get a flash across 1 or 2 pixels and at a certain intensity as well. And so the product itself takes all of those individual strobes along those pixels and combines them based on their location and their temporal proximity, and then makes an estimate of a single flash from that, and then uses all of the pixel intensities to try to estimate where the best guess of the center or where the strike point of that lightning might have been. And then it includes just a single point reference for that individual lightning flash and what an intensity, potential size, and location is. An interesting thing to note for this, just looking at it, is because you're looking at relatively large pixels, that usually lightning is only occurring in 1 or 2 of those pixels per flash, and you're averaging across those, you get a lot of bias in the latitude and longitude estimates of where those are. So it's just something to be aware of when you're looking at that you need to take into account the area spread of the individual flashes if you want to do make any sort of predictions with this data product. So for this, we actually didn't use our satellite that we had here. We went back to NOAA and collected their lightning product. You get about 4,000 files a day, converted those out of NetCDF and into CSV, which gives you about 100 million lightning strikes per year in the Western Hemisphere that GOES covers. Gross subsets of that can get us down to about 750,000 strikes per year in the area around California. That includes parts of Nevada and the ocean as well. And then we finally put that into a Postgres database so that we can give a data product that has that can be added into GIS systems like QGIS. And then we added quantization functions so you can convert from the quantized data to real units. And so an example of this, it's again, and we'll be talking about the 2020 August lightning siege. By far, most of the lightning that's strikes California during the fire seasons are in the mountains, in the Sierra Nevadas or the Cascades or in the Klamath Mountains. But you do get these very anomalous effects. And so the one that we heard a lot about in the last presentation, and I'll talk about too, is this what's considered the 2020 lightning siege. So in the middle of August, the 15th, the 16th, and the 17th, we had very dry, hot conditions across all of California, and we were hit by these thunderstorms that rolled through with very little precipitation, but very, very active lightning storms. And you can see on the left, we're looking at August 15th, and then we're going through the 16th and the 17th. And the yellow and orange areas show those GLM strikes where we've spatialized them over the predicted area from each individual point, and then found the density. So you get a nice little heat map of where the most of the lightning was striking. And then you can compare that to the individual dots there that are showing where CAL FIRE actually identified lightning-related wildfires that started on those particular days. So it's very easy to see that as these 3 days progressed and the lightning moved to the north, the number of lightning strikes that started wildfires over California was moving in the same direction. And this was the 2020 was very active. CAL FIRE acknowledged about 500 fires, 42 of them or 40 some odd of them happened in these 3 days. And as we saw, some grew to quite dramatic size as well. So what this makes you think is that it would be great is if you had real-time access to this kind of data so that you could maybe see the lightning as it was moving into California or that it was moving across the state, and you could combine it with these other external data products like what the fuel load or the moisture content is to really identify these hot spots that you really should be concentrating on. And that's what we're doing with the system that we're developing here. And so here's an example of that. Now, if you want to do processing with that lightning data, you can just set up a normal Python Jupyter style notebook, connect to a web socket, connect that socket to the data that we have available here. And then every lightning strike that will come, you'll get this kind of JSON representation of it. And then from this, you're able to do the kind of processing that you might want to do in real time, combine it with other data products and whatnot. And so that's kind of a good motivation for the system that we're looking at. Our system is called CASITA, which is California Spatial Imaging, Streaming Imaging, I guess, for terrestrial applications. And it's a combination of a GOES-R weather satellite that exists on the UC Davis campus and some processing that we're doing here at the library. And really, basically, it's kind of just a speculative research project that we have here at the library, wondering about how we can push the library's role in providing research data access. And I guess since we know that I came from land, air, and water and have been working in that, it's kind of obvious that I have a strong desire to see the library have more of an active role in this kind of data. But we have a lot of other components to that as well. A strong partnership with DWR that actually maintains that GOES station on top of Kemper Hall as a backup to their production system in Sacramento. In-house domain knowledge about how the GOES data products are working through this evapotranspiration. But as I said before, since there are so many bands of GOES and there's so many potential data sets that are available, the potential for using this data in real time across multiple different departments and projects is really high. And so we'd like to see what we can do in that area and kind of share this across the campus and really the West Coast researchers. And it is a fair amount of processing that's done for the GOES to process GOES-R. We're putting about 500 gigabytes of data per day onto disk to make that available. We don't retain that for very long. We keep that up currently for about 48 hours for all of the data products that we're recovering. And then for some of those go into a longer term storage stream. At any one time, we have up to 30 CPUs that are running and about 100 megabits of cluster on that, which scales a little bit depending on load. Almost all of that is actually to do the decoding and the posting the ABI images. So I said before that the imagery is the most important component of the GOES satellite. It's also by far the most data intensive. And so we're constantly just downloading those packages and creating components of an image and then putting them together. But there's lots of other processes that are running along in that same area to do message processing, to keep track of database information, and to interact with the researchers and the other services. In terms of the way that the processing works, the workflow here for our CETA project is that originally you have all of the data coming in directly from the GOES receiver that is here on campus. And when that comes in, it can be any number of different types of data, and the packages are all different based on what the underlying data is. So you might have XML products that just are describing the state of the sensor. You might get an image for a particular band over the full disk scan from GOES. You might get a couple of lightning strikes that come. Then you might get another band from a CONUS, the continental US scan, or a second band from that. There's also a mesoscale scans, which is why California gets so many scans, because usually that small area scan is over California. What happens after that is that we take each of one of those individual packets and process them. And so at that point, we have tiny little fragments of all of the images and the other little data products. And at that point, we can start to develop system health dashboards. So we can make sure that we're keeping up with all of the data as it's coming through the system, for example. But the next component that comes from that is that we're taking all of those individual fragments and we're putting them together into bigger blocks that are more easily used by researchers. And at that stage, that the data becomes more and more useful as a product that can be developed into further sort of value-added things. We use that locally for our own dashboard, where we're showing the real-time aspects of the GOES satellite imagery. Then it continues on where we compose out those into even larger areas, clip out California so that we don't have to save all of the imagery, only kind of the areas that we're interested in, and make those available for archiving. But then the final part is that because we're getting this data in so quickly, and that you don't need to necessarily wait for an entire scan to come in, we can build event detection sort of items on this as well. And so I talked a little bit about potential incidents from the lightning mapping system, but you could build similar types of real-time applications to look at things like wildfire starts or inundation events, for example. So this is another example of the data products that are available. So this, on the right-hand side, we see a mesoscale image of California. And at this, on the left-hand side, we see all of the different products that are available through a standard HTTP interface. So at the lowest scale, as each individual fragment comes in, which is just a small number of pixels for this image, those fragments are available immediately. As those fragments complete a block of imagery, that block is calculated. And then when all the blocks for a particular area, like for this particular mesoscale image are completed, then those complete images are also made available. On top of that, we've added event monitoring as well, so that you can actually see all of the new data products as they're becoming available on the system. And we provide two separate types of streams for that. We provide an HTTP access that's a stream provider, and then we provide a similar access via a WebSocket library. And for the HTTP protocol, you can go to a URL on our data site and just get every single event as it's happening. So get notified of every event that's happening as new data is being added to the system. But what you can also do is build templates. So if you're only interested in a particular band or a particular area of California, then you can fill out a template that shows the only components that you're interested in. And when you do that, the stream that comes back to you is tailored to that template. So then you can listen to that stream. As you get notified of new events, you can go and download the data and add it into your processing system. The WebSockets works in a similar way. The access to that is authorized. You actually respond when you acknowledge when you've received new events. And it's a little closer to the underlying internal Kafka streams that we're using in our processing system as well. But I want to show another demo application of how you can use this data in order to come up with event monitoring. And this is using band 7, which is a shortwave infrared. It's kind of the band that most clearly shows wildfire detection. And in this case, we're actually not doing a full algorithm for trying to find new wildfires, but instead we're just looking at thermal anomalies. So for every band 7 image that's coming in, we're keeping statistics for the last 7 days about how that pixel has behaved in that previous time frame. And then for each time a new image comes in, we compare the pixels to the expected statistics of how they behaved before. And if they come out that that pixel is particularly bright or hot in comparison to what was expected, then the system will actually build a small KML file, which is a GIS, sort of a digital map that's very easy to read in multiple different spatial environments. And then it will actually put a notification on a Slack channel at the library. And so this is kind of filling out that, demonstrating that last bar that we showed before, where we're taking the data and as quickly as possible building events that are more parsable by the decision makers in the system. And this shows an example of that in action. So in the upper part of this, you can see the notification that comes on the Slack channel that there's a new thermal event. If you're interested in that, you can download that KML. Here we've put it into Google My Maps as a good example of that. You can see on the left-hand side the pixels that were involved in that particular identifier, and then information about where it was located and the particular values. And then if you click further on, you can actually see the historical statistics that were used to identify that this was an anomalous item. The Casita dashboard that we have is also a good demonstration application of all of those tools. It's looking at the exact same API that we make available to all of our researchers. It's using the HTTP streams. Anytime you select a different band on the left-hand side, it'll modify the template, listen to those events as new images come in for each individual block. They're put into the system and kept an up-to-date image of the current processes, or the current imagery for California. Finally, some of the lessons that we've been learning in developing this application and maybe some of the next steps. Technically, on the technical side, we've learned that it's really important for us to do monitoring of the process from as soon as we can, because when things go wrong and you don't have good logging of what is happening, it's very hard to unwind and decode what went wrong, which is really important when you're trying to work in a streaming system. It's giving us a good idea of trying to scope out what the next sort of pieces that we should be developing are, and not try to take too big of a bite off, but take kind of smaller components and make those available. For example, instead of creating new complete products, we're thinking of our next step being sort of intermediate products where we'll calculate band ratios or differences on the machine and make those available directly as well. And then these messaging systems to try to come up with simplified ways to get the data to the researchers is really important. From the science side, the GOES data products are hard to replicate. The theoretical documents behind them are not really code, and so you have to sort of start from scratch when you're building your own system for that. And there's a lot of external data requirements that are done with that as well, which kind of leads back to the idea of scoping these problems and kind of making sure that we can pick the next most important step. And then we're excited to see whether or not some of these interfaces that we're developing that make it easier for researchers to incorporate the real-time data quickly can help to jumpstart the development of the types of products that we're looking for. We're also interested in AI applications and have been reaching out to various people on campus to see about, since you have so many images, is it easy or is it possible to do predictive forecasting just from machine learning of all the code that you see. And that is it. Thank you very much. I'm happy to take questions.
Thank you, Dr. Quinn, for the presentation. So we have two questions. So we will take first question. It says, it is from Evan, and it says, are you saying that with this data, one might be able to develop a fire potential index that considering parameters such as fuel type, loading, weather condition? And there is a second question on the same, where a fire agency could focus their attention. Can you elaborate on that?
Okay, I'll answer, I guess I'll just answer the second one first, and then I'll go up from that. The GLM is different than surface lightning monitoring systems in that it cannot tell the difference between cloud to ground and cloud to cloud events. Ground-based lightning systems can do that pretty accurately, and that's something that you can't do from the GLM, since it's based basically on a straight down visualization of the actual lightning. Where it can become more valuable is, as it kind of alluded to, is if you're able to follow GLM activity, perhaps with other cloud activity as storms are coming in from the ocean, that might be an area where you get some additional benefit from that. And just also the fact that we're hoping that we can integrate our GLM product into real time in a way that's simple to use, even if it's not maybe quite as good as the ground-based lightning detection systems. For Evan's question about asking if this data people can develop potential fire indexes, yes, but also at the same time, we think that this could actually, you might actually end up developing a lot of these fire potential indexes, like the fuel type and the loading, with using other products, like potentially using Landsat imagery. So you might be developing your fuel type or your fuel moisture by looking at other imagery products. What we hope to be able to do is then combine that with the real-time data that you might be able to get from GOES. So you could develop, for example, an application where you have your own fuel map and your own moisture conditions that you've got from Forest Service or somewhere for that particular week. And then as these lightning storm events might come in, you can combine those and identify the areas that you might be most concerned about. That being said, I think there probably is something to be said about using some of the GOES data products to do things like fuel moistures, fuel skin temperatures, and some other products as well.
Okay, so there is no more question. So I think we will conclude your presentation, and thank you very much.
Thank you.
So now we have a break. So I think let's meet at 3. Hello, everyone. Welcome back from the short break. and I hope you are enjoying the symposium so far. So without wasting time, I will start next session of the symposium, and we have Dr. Mikhail Barbato for the presentation. Dr. Mikhail Barbato is a professor of structural engineering and structure mechanics in Department of Civil and Environmental Engineering at UC Davis. He is also co-director and co-founder of UC Davis Climate Adaptation Research Center. He received his summa cum laude laureate degree in civil engineering from Sapienza University of Rome, Italy in 2002, and his master's and PhD in structural engineering in 2005 and 2007 respectively at University of California, San Diego. He is a licensed professional engineer in Louisiana and Italy. He is an expert in both traditional and innovative construction methodology and material, with particular emphasis on new, recycled, and green material. His research include modeling, analysis, design of structure and infrastructure systems subjected to earthquake, wind, storm surge, and wildfire hazard. He is active in development of performance-based methodologies in earthquake, wind, hurricane engineering, as well as in multi-hazard application. Dr. Barbato's research also embraces nonlinear finite element modeling and analysis of structural system, random vibration theory, structural reliability analysis, multi-hazard assessment and mitigation under current and changing climate condition, life cycle cost optimization of resilient and sustainable structures subjected to multi-hazard. His research aimed to develop safer, economical, and more rational design procedure, accounting for natural and man-made hazard, which supports the development of sustainable infrastructure and more resilient community under current and changing climate condition. His research, teaching, and service activity has a strong focus on justice, equity, diversity, and inclusion principle. With this, I invite Dr. Barbato for his presentation.
Thank you very much, Nitin, and let me thank everybody that is staying with us after a very long day. I hope you enjoyed the previous presentation, and I hope I will end on a good note. I'm going to present our current work on wildfire risk mitigation in the wild and urban interface, from ignition resistant to fire resistant houses. This is really a research that is very dear to me. Been working on using these type of structures for more than 10 years. And I just shared my screen. Before I continue, I want to make sure that everybody can see my screen and can hear me correctly.
Yeah.
Yes, looks good. Thank you.
Perfect. Thank you. Appreciate it. And so really this work is on the idea of making structures that can take wildfires and survive, not only survive, but also survive in a way that they can be used again in a safe manner. I will start with a brief introduction and background, explain what type of structure we are talking about. Fundamentally, we are talking about earthen structures. And then I will provide some research updates that are advancement of this technology that we are doing with the support of this project, in particular in terms of modeling and in terms of improving the ductility of the material using the natural fibers. And then I will present some preliminary results on the wildfire resilience of earthen construction, as well as give some indication on the ongoing and future work that we are doing with conclusions. So what is that we are proposing here? We are really proposing to get back to something that is an ancient technology that has been almost forgotten in the last 100, 150 years, at least in economically advanced countries. We are talking about going back to the use of earthen structures, which are buildings that are built using mainly soil with other possible mixes, but fundamentally soil. This is a very ancient technique. It's also a very sustainable technique. We have been using it for more than 10,000 years. We have historical rests of towns that were built using the soil. We have more modern applications that are also available. Some examples here of the city of Potosí in Bolivia that has a lot of constructions that are made with soil. And then the Pueblo, the Taos here in the United States, constructions that are available in Africa, in Asia, in Australia. Many of those are UNESCO World Heritage Sites. Still about 30 to 50% of the world population lives in earth-based dwellings. And this is really everywhere in the world. However, even given that, we know that the technique of using soil is not the most common technique, at least here in the United States. So let's go back to a little bit of the story and the typology of this construction. Historically, there are three different ways of building with soil. The first technology is cob, where soil is mixed with water, generally with natural fibers. Then it is made into a slurry that is posed to build the walls in layers. These layers are then left to dry to the sun until they become a monolithic element that can provide strength and support for the structure. In rammed earth, the technology is slightly different. The soil is compressed together using forms and machinery that compact the soil in place, building these walls. A big example, a very famous example of rammed earth wall is the Great Wall of China. And then we have adobe, where the soil is packed into blocks. Again, there is usually a mix with the water, with the straws in order to provide some additional ductility to the material. These blocks are then left under the sun until they dry up, and then they are used to build the structures using typical masonry techniques. These are the historical methodologies that are used. They've been used again for a very long time. They are still used, but we are focusing on a modern version of earthen construction that is a more engineered version of it. And we are talking about earth blocks. Earth blocks that exist in different forms, in different flavors, let's say. We have compressed earth blocks where the soil is mixed with water, generally with other fibers or other materials, in order to be compressed mechanically, produce the blocks, and generally this increases the mechanical strength of the material. Then there are stabilized earth blocks where the soil is mixed with the chemical stabilizer, generally lime, sometimes cement, and then without any additional compaction are again left to dry at the sun. The reason of stabilizing chemically the material is to introduce a higher resistance to the weathering of the material, so to produce a better durability. And then these two techniques can be combined to obtain compressed and stabilized earth blocks. And this is really the focus of the research that we are performing here at at UC Davis. There are wonderful examples of modern constructions that are done using this technique. Several houses, buildings, schools, again around the world, that are being used and are performing in a very good way under different types of hazards. So how do we produce these blocks? Here I wanted to just show the different forms, shapes that can be given to these materials, and an example of our students making a block with a machine that we have actually built our own ourselves in our lab. This is a modified version of a compression machine called the Symposium that was developed in the 1960s. As you can see, this is kind of a laborious process with that original machine. More recently, we have purchased an hydraulic machine, an Auran press, that allows to do all of this process in a mechanized manner. And so in terms also of production of our blocks, we went for from about 30 to 35 blocks per hour with 3 people working on it to about 300 blocks per hour using this machine. And again, with different forms, we can provide the different shapes. These are just some of the examples of the blocks that we can produce with our machine. In previous research, we have focused on investigating the feasibility of this type of construction, particularly for a combination of different types of feasibility. First of all, we wanted to make sure that the structure that we are building is feasible from an economic point of view. And that is because it is not really clear the combination of the fact that the material that we are using is practically free. We are really using soil. All we have to do is take it from under the ground and use it for building our blocks. However, again, there is a labor component that is involved. And from this point of view, we investigated the houses in southern Louisiana subjected to very severe winds coming from hurricanes and tornadoes. And we were able to develop a new construction technique based on interlocking blocks that are connected without using mortar, that reduces the labor necessary to build houses by a factor almost equal to 2. And with this new technology, we were actually able to build houses that were not only significantly more resistant to winds and other actions than the typical light frame wooden house that is generally used all over the United States. But we were actually able to build or to design a wall that can be built at a cost that is lower than the one of a light frame wooden house. And we were also able to develop here an example of a test that we performed on a wall. We developed the stucco made with a mix of soil and cement that can be used to protect the surface of the wall under severe rain and wind like the one typical of southern Louisiana. Actually, a very interesting result of this research was that the side of the wall that was protected, as you can see from this little video, not only didn't have any visual damage after about 180 days of really bad weather in Louisiana, but actually the blocks of the side that was protected with this stucco, they kept increasing their strength and they became better and better with passing of time. So starting from these very encouraging results that are really telling us we can build houses made with soil that are cheaper, stronger, and more durable than light frame wooden houses, we started investigating other issues that are making difficult the use of these type of construction. A first issue that we investigated is how to model the performance and the mechanical behavior of this type of structures. In general, the methodology used for masonry is based on a finite element modeling technique, and particularly the most commonly used methodology is called the simplified micromodeling. In this case, what is done is really decompose a wall or any part of the structure into expanded units and zero thickness mortar joint interfaces that are representing the mortar joints. The basic hypothesis of this technique is that the mortar is significantly weaker than the units. And this is generally true for ordinary masonry, where the units are concrete blocks or they are fired clay materials, and they are significantly stronger than the mortar. However, we knew from existing experimental results that these conditions are not satisfied for earthen construction. That is because the mortar is made fundamentally by the same material that is used to make the blocks. And so the strength of the two components is really very similar. We posited that in order to be able to actually understand and predict the mechanical behavior of these type of structures, we needed to do something better than a simplified micromodeling. And we proposed to use what is called a detailed micromodel, where the masonry units, the mortar, and the interface between units and mortar are all modeled explicitly in the finite element in order to represent all of the possible masonry failure modes that are typical of masonry structures. So what we found is we applied this new technique first to ordinary masonry to see if we were still getting good results. And here you have a comparison really between experimental data that are the solid black lines and the numerical data that is representing a shear test on a wall for which experimental data are available. And as you can see, we had a very good agreement between our numerical prediction and the experimental data that were obtained from two nominally equal walls built using ordinary masonry. In a certain way, as expected, we found that both the simplified micromodeling technique that already exists and the detailed micromodeling technique that we were proposing were producing very similar results that were in good agreement with the experimental results. Even though we found that as we were increasing the vertical load applied to the wall, and so we were increasing the state of compression stress inside the masonry, we found that the detailed micromodeling approach was keeping the same level of accuracy in representing the experimental results, while the simplified micromodeling approaches were in a certain way degrading and not able to capture as well the experimental behavior. Here in all of these three figures are represented again with a solid line, the experimental results, under three different level of pressure applied at the top of the wall that you have seen before. And then all of the others are, all of the other curves are representing the numerical prediction of this experimental behavior, with the blue line, the blue solid line that corresponds to the model that we had just proposed. At the end of the day, anyway, we found that the level of errors for the detailed micromodeling were lower, but not significantly different than the results that we were obtaining using the simpler and the less computationally expensive simplified micromodeling. However, the next step in order to prove our hypothesis was to apply all of these methodologies for numerical analysis to a structure made using earthen blocks. We identified experimental results that were available in the literature, and we used these different simplified micromodeling techniques, as well as the detailed micromodeling techniques that we have presented, in order to, again, predict the experimental behavior of these wallets that were tested in diagonal loading with the load that is applied as a displacement in this direction. And this is what we obtained. The yellow line corresponds to our simulation with the lighter color along these figures that shows the prediction obtained using the detailed micromodeling in terms of the cracking within the structure. And qualitatively, you can see that there is a very good correspondence between the experimental results and the numerical simulation that we obtained with our detailed micromodeling. You can see that when we have tried to understand not only the deflection, the form of the cracking, but also the peak strength that we can obtain with these walls, our new model, the DMM, produces much better results than the simplified micromodeling techniques that were in all of the different possible flavors, always overestimating the strength of the walls, which obviously is a reason of concern, because if we were designing a wall using these techniques to predict the strength, we would be over-predict the strength, which means that we would be on the side of not being safe. So with this new technique, now we can actually predict much better the actual strength of earthen block constructions. The other issues the other issue that we wanted to resolve for this type of construction is the intrinsic brittleness of soil-based materials. And historically, the technology that has been used in a certain way empirically since 10,000 years ago was to mix the soil with the natural fibers, with straws or other natural fibers. And so we caught the opportunity to use a material that is fundamentally an agricultural byproduct, or in some places actually a agricultural waste that is very abundant. And this is the sugarcane bagasse fibers that are obtained from the production of sugar. We are talking about a huge amount of fibers, more than 400 million metric tons per year produced of fibers from the production of all of the sugar in the world. This is actually quite abundant also here in the United States, particularly in Louisiana, in Texas, and in some part of Florida. And so our hypothesis here is that we can improve the brittle behavior of compressed and stabilized earth blocks by using fibers obtained from sugarcane bagasse. We did all our experiments, investigated three different aspects of the strength, the flexural strength of blocks that are built using different amounts of sugarcane bagasse fibers. These are blocks that are considered with three different levels of cement, 0%, 6%, and 12% in weight of the original material, with an addition of bagasse fibers. The control is with the no bagasse fiber, then 5% bagasse fiber and 1% bagasse fiber. Notice that actually 1% bagasse fiber is in volume, is expressed in weight, but when you transform it into volume, is a significant amount of the volume of the block, simply because the bagasse fiber is significantly lighter than the block. So the results were in a certain way not surprising because we obtained a significant improvement of the ductility of the material in flexure with the addition of bagasse fibers. The same way we had an increase in the ductility and the toughness of the material in compression. There are the two effects of cement amount and fiber that are in a certain way contrasting, because with the increase in cement, you increase the strength, but also reduce the ductility, and thus the addition of bagasse fibers allows you to increase the strength without reducing the ductility, which is very important whenever you want to build something that resists lateral loads like earthquakes or hurricane wind loads. We also did a durability test on this material. In a certain way, we also expected this type of results, that by increasing the amount of fibers, we were decreasing the durability of the material. But at the same time, by increasing the amount of cement, we are increasing the durability of the material. And so there is a sweet spot that increases the strength, increases the ductility, maintains the durability, and is not excessive in terms of the additional cost of emissions used to produce cement, so that we can optimize the composition in order to improve the performance of this material. Now let's go into the core of the presentation. Now that we are not only confident that our material can be obtained in a way that is economically feasible, structurally feasible, that can be analyzed in a way that allows us to actually estimate the appropriate strength, we wanted to use it to make houses that do not burn. And I'm not going to spend a lot of time on this, but we all know, and we have seen during the series of presentation today, that wildfires are getting worse and worse with issues that are connected to climate change that are increasing the hazard, and also with the fact that we are building more and more houses in the wild and urban interface in the WUI, which is increasing our vulnerability, which has a total effect of increasing very rapidly our risk associated with wildfires. Now, another thing that is interesting to notice is that the amount of damage and losses that are connected with wildfires is not as strongly correlated with the amount of acres burned by the wildfires, as much as it is correlated with the number of structures that are damaged or destroyed. And there is also a very strong correlation between the losses and the number of losses of life. So resolving the problem of housing that are not burning may not solve the problem of wildfires in terms of acres burned, but it would have a huge impact in terms of saving lives and saving property, which is fundamentally one of the core interests of state agencies, and I would imagine of the general public. Saving life, saving properties, and then saving the ecosystem are really where we should put most of our efforts, at least in my opinion. Here I'm just showing how the severity of wildfire hazard is increasing. It's expected to increase due to climate change. I want to focus more on what are the mechanisms that are really conducing to the loss of houses in the WUI. There are three major mechanisms. The first one is the direct contact with the flames due to surface fires. This is really connected with flammable or combustible materials that are near the house. The fire reaches the house, and once it reaches the house, It burns the material because the houses are made with wood, and wood is combustible. And so if subjected to enough contact with flames, they will end up burning. The second mechanism is heat radiation due to crown fires. In this case, actually, the fire is not in contact with the house, but increases enough the temperature to produce combustion internally, or even in the materials that are making, of which the house is built. And then there is the third, probably most insidious phenomena that produces ignition, that is ember attacks. These are firebrands that are conducted by wind. They are burning, and this is where really detailing is most important, because embers will find the weakest spot, that will penetrate inside the house. And once they penetrate inside the house, they will produce burning, because the material inside the house will always have a component that is combustible or even flammable. So in order to save a house, we really need to combat all three issues of ignition mechanism. The approach that has been used so far is to make houses that are ignition resistant. Ignition resistant means that it is difficult to start a fire, but the materials can still burn. And in fact, you can see if you go into chapter 7A, that is really the building code for California for building in the WUI, all of the different materials are approved according to fire resistant test standards that are providing a resistance for periods that go from 3 to 30 minutes. Then the next layer of protection is really provided with the exterior protection and with defensible space. There are two legally required defensible space area at 100 feet and 30 feet around the house. And there is a third one that will become required, that is at 5 feet around the house, where no combustible or flammable material should be ever located. Our recommendation is to go from a ignition resistant house to a fire resistant house, a house that really doesn't burn. And this is really guided by the fact that our material, as you can see here, when you compare the effect of putting a propane torch at 3400 Fahrenheit near the material that we are using to build walls and houses does not burn, it's not combustible. We have tested this material in a furnace at 1800 Fahrenheit, and after 7 hours, the material is still maintaining its form, its shape, and part of its strength. We are actually doing more technical investigation to understand exactly where we are at in terms of the strength. These are some of our blocks that we have tested. We investigated the composition of the material. This is actually soil that was taken from Paradise after the fire of 2018 for investigating what we can use there to rebuild houses in a different way. And we did our high temperature test by putting our blocks in a furnace and then heating them at increasing temperature for even longer and longer period of time. We arrived up to 7 hours of fire heating at 1000 Celsius, about 1800 Fahrenheit. So what are our results? First of all, what we find is that the different blocks subjected to different temperature are cooking. What we were not doing in terms of production is happening because of the fire, and we are obtaining fundamentally fired clay that is going from the outside and then reaching deeper and deeper as the temperature and the duration of the fire is increasing. Then we did flexural tests. And what we found in the flexural test is actually that the modulus of rupture and the modulus of elasticity of the material are decreasing as the time and the temperature increases. And this is fundamentally because microcracks are forming inside that are producing weaker spots where the fracture is going to propagate. We did also our compressive test, and here we found something that in a certain way should have not surprised us, but it was still surprising because actually the strength of the material is increasing as we are increasing the temperature. Again, we are obtaining now fired clay bricks, and we actually exceeded the capacity of our compression machine with testing the blocks that were subjected to 600, 800, 1000 Celsius. And so we are readjusting our setup to a machine with the higher capacity to complete our tests. And so that's really what we obtained with the compression test, is that the strength is increasing, the material is getting better with the fire. And that is very promising in terms of ensuring that the house that we are building are not only not going to burn, but also are safe to be re-inhabited after the wildfire has passed. Some of the work that we are still performing, obviously, we need to complete this experimental testing of blocks under uniform heating, but also we want to investigate what happens in terms of gradient of temperature. In particular, we are interested in performing an ASTM E119 test that is a combination of gradient temperature plus the effect of a water jet to reduce drastically the temperature on one side of the wall. We are investigating the thermal properties of this material. There are two issues here. One is the thermal properties can be very useful to produce energy savings in terms of heating and cooling. And then under effect of severe wildfires, they are also ensuring that the temperature in the indoor does not change even when the temperature outside is very high. This is fundamentally protecting almost in a complete way from the first two ignition mechanisms that are typical, the direct flame and the radiant heat. Obviously, we still need to be careful with vents and with the appropriate materials in the roof in order to take care of the problem of embers. And then we are doing evaluation of the emissions under wildfire conditions. This is something that actually was shown before in the presentation by Katie from Los Alamos National Labs. And what we found is that our material has almost no emission because it doesn't burn. And if we actually evaluate the embedded energy of different structures made with different materials, and then we account for the carbon produced by burning these materials, we found that light-framed wooden houses that are significantly more sustainable than concrete block houses or sandgate block houses, when just by considering the building phase, are not that good once they burn, because you have actually a similar production of carbon and you don't have a house anymore. It's burned. With our construction, there are almost no emissions, and the embedded energy to start with is similar to the one of wooden houses. But then there is an additional energy savings of the order of 30 to 70% in terms of heating, cooling, and humidity control. That is in addition, an additional advantage that wooden houses generally do not have. So I'm going to conclude. I think actually I'm a little bit beyond my time. We have already demonstrated that earth and masonry represents an affordable, safe, and sustainable techniques for construction of houses and low-rise buildings. We have developed a finite element modeling techniques based on detailed micromodels that allows us to accurately predict the mechanical behavior of this type of structures. We have demonstrated that natural fibers can be used to improve the ductility of the material, which is very important for seismic and for wind applications. And research is ongoing to develop all of the different aspects for an affordable fire-resistant construction technique that is based on compressed and stabilized earth blocks. This is because this type of material really shows great potential to address climate change in a way that is also equitable and that promotes economic development in an equitable manner. And we are focusing on wildfire resilience and the mitigation of wildfire smoke emissions that is produced by using techniques for construction that are resistant to wildfire. Some acknowledgements, obviously the UCOP Lab Fees project that is funding this research and is supporting today's symposium. Also projects that were funded by the National Science Foundation, by the Louisiana Board of Regents Economic Development, the Louisiana State University Coastal Sustainability Studio, and then different collaborators from University of South Carolina, from Louisiana State University, and Dr. Nitin Kumar, that really is the person that did most of the work that I presented today, and the numerous undergraduate students at UC Davis that have been very, very enthusiastically working on this project. And with this, thank you very much, and I'll be very happy to respond to any question you may have. Thank you.
Thank you, Dr. Barbato, for your presentation. And we have actually one question, and it says, have you tested the material for seismic safety?
Thank you very much for the question. This is a very good question, and yes, actually we did quite some work on seismic resistance of this material. The two NSF, one of the two NSF projects was exactly to understand the performance model and test experimentally the behavior of these type of constructions under seismic loads. We have come up with the way of designing these masonry structures in a way that they can be safe also under seismic loads. Generally, it requires reinforcement. We have used fundamentally only steel reinforcement, even though we are looking for funding to investigate other more sustainable techniques for reinforcing, for example, bamboo or other natural type of reinforcement material. But we have not done that research yet. However, by using typical steel reinforcement, we have been able to design structures that are still economically feasible up to 2-story height, even in high seismicity zones. And so it is possible. It requires understanding of seismic behavior, and we are still working on the calibration of the parameters that can be used for actual design in seismic zones, but it is possible, and we have done quite some research. I have to add that there are actually several other groups spread around the world that are doing research on seismic performance of earthen constructions. This is because a lot of earthen constructions exist in places that are very highly seismic zones. For example, there are researchers in Chile that are investigating external reinforcement using very cheap technologies for retrofitting existing houses. There are research groups that are investigating the performance of these structures in places like Turkey, where again they had a lot of houses failing under earthquakes because we're not really engineered to resist seismic loads, and so they are providing guidance on how to do that. There are researchers in Europe, particularly in Portugal, that are doing quite some interesting work on the seismic performance of earthquake construction. So it is a very wide, interesting, and I would say promising, not only research topic, but application that could really change the way that we are building houses in the world. And let me add a piece of information that I think is important. We are expected to need about 2 billion new houses all over the world in the next 50 to 80 years. This is to account for both the growth in population and also for the improvement of life conditions all over the world. This is a lot of houses. And if we keep building houses that are not performing well, that are not providing sustainability, that are not giving enough energy savings, we will have a very big issue in trying to reach the goal of net zero anywhere in the world if we don't take care of buildings and housing and find a way to build them in a more sustainable manner that is also safer and can help population deal with natural hazards that are like hurricanes, earthquakes, and wildfires. But thank you very much for the question.
Okay, so I don't think we have any more questions. So I will request you for the closing remark on the symposium.
Thank you, Nitin. So Olivia, I think you have control. Oh, perfect. Thank you. So at this point, I'd like to really thank everybody for staying till the very end. I wanted to just give an overall overview of other things that we have accomplished so far with this project and that we just didn't have the time to put in a symposium by keeping it within a single day. But in terms of accomplishment, we have already published several articles. We have submitted, we have 9 journal articles, 2 have been published, 1 is in press, 6 under review. Considering that the project started less than 2 years ago and we had a pandemic in between, I think I really have to acknowledge the great work that the team has been doing under very difficult conditions. We also had 7 conference articles, peer-reviewed conference articles. We've been extremely successful in leveraging the research grants from other grants and producing new proposals that have brought additional funds. So there are other 10 grants that are connected with the work of these UCOP Lab Feeds project for a total of 14.2 million approximately. We have tried to contribute as much as possible from the knowledge that we are gaining in this project to provide information to state and federal agencies and address their needs. We have participated in a legislative briefing webinar, How to Predict and Manage California Fire Risk in a Changing Climate. We have participated in the 2nd annual statewide forest science research coordination meeting for the state of California. We have provided presentations for the UC Wildfire Symposium #1, #2 that were organized by the Office of the President of the UC system last summer. Next slide, please. We have been very active and effective in our mentoring and educational activities, developing science and helping young scientists to succeed in their career and their research. We have mentored more than 20 undergraduate students, researchers across all of the different institutions. 7 PhD students, 2 of whom have already graduated. There are other students that will be joining our team very soon. 8 postdoctoral researchers and 5 between junior faculty and researchers. As we have discussed across and during the presentations, particularly at the beginning of the symposium, we had a very strong focus on diversity, equity, inclusion, and justice. And we have participated in activities that are not necessarily within the scope of this project, but that are helping us to favor and really give the idea of how important is climate justice for everybody, not only for the people that are directly affected. So we participated in the Citrus Diversity in Tech Symposium that was that took place not long ago, a couple of weeks ago. We are developing and updating new modeling characterization tools that are being made available or will be made available to the general research community. We have seen Casita today, QS-FIRE, the combination of WRF, S-FIRE, and CHEM. These are all new contributions that are really for the benefit of the entire research community. Next slide, please. And here we are really talking now about what we are planning to do. We are building an international collaboration with CSIRO, the colleagues from the other side of the world in Australia. As you well know, issues of wildfires are affecting United States, Australia, and many other countries in the world. There are obviously differences, vegetation, climate, topography, but there are also a lot of similarities. And socially speaking, the problems produced by wildfires are the same everywhere in the world. And so we are really taking a multidisciplinary, but now also international approach to this problem to put together the best minds from different parts in the world to make a contribution and help in mitigating the most disastrous effects of wildfires. There will be also a third and conclusive wildfire-induced air pollution assessment and mitigation symposium. We are planning to have this symposium at the end of the project as a summary of all of the different accomplishments and the results that our team is developing. And sometime in 2023, February 2023, we are also planning a new conference that is called the Wildfire Resistance Structures Conference and Trade Show. This is really a new type of conference because we are putting together a wildfire conference with the trade show. And the idea is to provide not only our results in terms of science, but also make available to normal people, to the general public, but also to state agencies and policymaking experts, all of the technologies that are already available and that are under development, and identify where the gaps are on which technologies needs to be developed in order to really address the problem of wildfires in an effective way. This conference is organized in conjunction by the UC Davis Air Quality Research Center and the UC Davis Climate Adaptation Research Center, which are also two of the supporters of today's symposium. Next slide, please. With this, I'm really at the end of the presentation. I'd like to thank one by one all of the presenters that were here today, that took the time to prepare the presentation. We were all busy, and this is for most of us the period of spring break. But I really want to thank Alison, Katie, Catherine Collon, Katie Benedicts, Matt, Leroy, Will, Caitlin, and Queen for their presentation, Lei and Nitin for moderating the sessions, and Dean Corsi and Executive Director Crittenden for providing the introductory remarks and placing this research project and symposium within the larger efforts that are ongoing in the College of Engineering at UC Davis and in the CITRIS and the Banatao Institute. So thank you very much. I think I've been very, very happy with all of the presentations. I found them personally extremely interesting. I hope that also all of the attendees have found something of interest to them. And I'd like to conclude by thanking all of you for attending this symposium. It was a very intense day with a lot of technical content and a very broad range of topics covered today. And so I really thank you for providing your time, your feedback, and I wanted to add that we plan to make the recording of this symposium available within a couple of weeks on the website of the Climate Adaptation Research Center. We'll make also available PDFs of the individual presentation. Again, just we need a little bit of time to pull together all of that, but it will be made available. We are also planning to send out after the event, probably in a couple of days, a survey to understand what we did well and above all to learn what we can do better for next time. And with this, again, I'd like to thank everybody for attending, for participating, for presenting, and I wish the best and enjoy the rest of the spring break for those that are in spring break. I'll also be available for another 15 minutes or so if anybody has additional questions. And again, thank you very much.
I know people are beginning to trickle off, but if you do have any questions for Dr. Barbato, feel free to send them either in the chat or using the Q&A box. Again, I know some people are trickling off, and if you are heading out, then we wish you a happy rest of your day, whether it's morning or evening where you are. If you would like to ask Dr. Barbato any questions, feel free to send those in the chat or using the Q&A box. Because there's such a low number of participants at this point, you can also go ahead and raise your hand if you'd like. And I can promote you so that you can actually verbally ask your question if you would prefer.
And also, if you prefer to send an email, you can find me at mbarbato@ucdavis.edu. Thank you, Olivia. You're faster than me at typing.
So we do still have a few participants on the line. You may be brainstorming your questions. So again, feel free to send those in the chat or in the Q&A, or you can indicate that you can raise your hand and you can unmute yourself to verbally ask Dr. Barbato. It doesn't really seem like there are any questions, so we'll stay on the line for just a few more minutes and then probably end this Zoom webinar or symposium a little bit early. Again, if any questions come up after the symposium concludes, feel free to send Dr. Barbato an email as well. Well, with that, we will go ahead and conclude today's symposium. Thank you once again for tuning in, especially if you hung in there this whole time. We really appreciate your attendance, and hopefully you will have a chance to fill out that feedback survey that Michaeli mentioned. We would really appreciate any and all feedback. It's very valuable to us for planning the next phase of this symposium.
Thank you. Thank you very much. And I think I missed probably the most important person to thank at the end of the presentation, Olivia, for really pulling all of these together in a very short amount of time. and it was a great event because you are a fantastic organizer, and I wanted to acknowledge that right here because it's important and it's true. So thank you, Lydia.
Thank you. I appreciate that. And hopefully if you are new to the Climate Adaptation Research Center, you're able to join us on our upcoming events where you'll see Dr. Barbato and myself coordinating in future endeavors as well. So with that, we'll go ahead and today's symposium. Would you like to end? Okay.
Thank you very much, everybody. Have a good rest of the day and see you soon to the next event.
Bye, everyone. Thank you.